Hello there and welcome to Physics with William, a quiet place where the universe can be examined slowly, one small mystery at a time, while the day begins to loosen its grip and the mind settles into something softer. Tonight, we're going to look inside one of the most familiar particles in nature and ask a question that sounds simple until the answer begins to unfold. Where does almost all of a proton's mass come from? A proton is tiny beyond ordinary imagination, yet nearly every solid object around you owes most of its weight to protons and their close companions, neutrons. The chair beneath you, the walls around you, the cup beside you, and the body listening to these words are all heavy, mainly because countless protons and neutrons carry mass inside atomic nuclei. But when physicists added up the masses of the small particles believed to live inside a proton, the total came out far too small. It was rather like opening a suitcase, finding 3 socks inside, and discovering that the suitcase somehow weighs as much as a piano. Before we move any further, where are you listening from tonight? Perhaps you are somewhere quiet with the lights low and the room beginning to cool. Perhaps you're still awake in a busy city, or listening from a place where morning has already arrived. And when you think about weight, what comes to mind first? A heavy box, a stone in your hand, the pull of your own body against the floor. Most of us experience mass as something obvious. It is the stubbornness of an object when we try to move it, and the reason a full shopping bag is less charming on the walk home than it seemed in the shop. Yet inside matter, mass is not always where common sense expects it to be. If you find these slow journeys through physics relaxing or useful, you can leave a like and subscribe to Physics with William. It helps this quiet corner of science reach other people who may enjoy learning while winding down. You can also share in the comments where you are listening from, and whether it is late at night, early in the morning, or one of those uncertain hours when the clock seems to have stopped being helpful. For now, settle into a comfortable position. Let your breathing find its own pace, and we will begin with something small enough to fit inside every atom, yet important enough to account for most of the visible mass in the world around us. A proton sits at the centre of nearly every atom. Hydrogen has 1 proton in its nucleus. Carbon has 6. Oxygen has 8. Iron has 26. The number of protons tells us which element an atom is, which means the identity of ordinary matter is organised around these tiny positive particles. Change the number of electrons and you may create an ion. Change the number of neutrons and you may create a different isotope. Change the number of protons, however, and you have changed the element itself. Gold becomes something that is no longer gold. Oxygen becomes something that will not behave like oxygen. The proton is not merely another item inside the atom. It is part of the atom's name tag. For a long time, the proton was treated as if it were a basic building block with no smaller structure. It was small, stable, positively charged, and apparently content to remain at the heart of matter. Later experiments revealed that the proton has an interior. It is made from particles called quarks, held together through the strong interaction by particles called gluons. The simplest description says that a proton contains 2 up quarks and 1 down quark. That description is correct, but it is also incomplete in the same way that describing the ocean as water is correct, while leaving out waves, currents, foam, storms, and the occasional person regretting a decision to go swimming. The 3 quarks are often called the valence quarks. They give the proton its overall electric charge and help establish its identity. But the space inside a proton is not calm or empty. It contains a restless quantum environment filled with gluons and temporary pairs of quarks and antiquarks. These appear and disappear as the strong force moves energy around. Nothing inside the proton sits still in the ordinary sense. The quarks do not orbit neatly like planets. The gluons do not behave like little pieces of glue placed between them. The whole proton is a compact changing system in which motion, fields and interactions cannot be separated as neatly as objects on a kitchen table. This is where the puzzle of mass begins. The up quark and down quark each have a small amount of mass associated with them. Their masses arise through their interaction with the Higgs field, the field that became famous after the discovery of the Higgs boson. It is easy to hear that story and conclude that the Higgs field explains the mass of everything. In an important sense, it explains why elementary particles such as quarks have their own basic masses. But it does not directly account for most of the mass of a proton. Add together the basic masses of the proton's 2 up quarks and 1 down quark, and you obtain only a small fraction of the proton's measured mass. That is the surprise at the centre of tonight's journey. The ingredients appear light, but the finished object is much heavier. The missing mass is not hidden in an undiscovered lump inside the proton. It does not come from a tiny secret weight tucked behind one of the quarks. It arises mainly from the energy of the strong interaction, from the motion of quarks and gluons, and from the way these particles are confined within an extremely small region. In modern physics, energy contributes to mass. A system can weigh more than the simple total of the resting masses of its individual parts, because the energy stored in the system also counts. This idea can feel strange because everyday examples often behave differently. If you place 3 apples in a bag, the bag weighs about as much as the apples plus the bag itself. There may be a little extra energy in the warm apples or in the tension of the material, but it is far too small for an ordinary scale to notice. Inside a proton, the balance is entirely different. The quark's basic masses are the small contribution. The energy associated with their motion and with the gluon fields is the large contribution. The proton is heavy not because its pieces are individually heavy, but because the pieces are bound together in an intensely energetic quantum system. One useful way to approach this is to stop imagining mass as a substance. Mass is not a special material poured into particles like filling into a pastry. It's a property of a physical system. It tells us how much the system resists changes in motion, and it is connected to the total energy the system possesses when viewed as a whole. A proton at rest may appear still from the outside, but its interior is anything but still. Quarks and gluons carry momentum. Gluon fields store energy. Quantum fluctuations continually reshape the distribution of matter and force inside the proton. All of that internal activity contributes to the mass measured from outside. Imagine a sealed box containing objects moving rapidly in every direction. If the box is perfectly closed, the motion inside does not make the box travel across the room, because the different movements balance one another. Yet the energy of that motion still belongs to the box as a complete system. In principle, a box containing energetic motion has slightly more mass than the same box when everything inside has less energy. In normal life, the difference is absurdly tiny. Inside a proton, there is no calm version in which the quarks simply sit down and have a rest. The energetic motion and the binding are part of what the proton is. Remove that activity, and you do not get a lighter proton. You no longer have a proton at all. The strong force responsible for this behavior is unlike the forces most familiar to us. Gravity becomes weaker as objects move farther apart. The electric force also fades with distance. The strong interaction between quarks behaves in a more complicated way. At very short separations, quarks can behave almost as if they are relatively free. As an attempt is made to pull them apart, the interaction does not simply fade away. The energy in the gluon field grows. Eventually, instead of releasing a lone quark, the system can produce new particles. Nature appears determined to keep quarks confined inside larger composite particles. This confinement is one reason the proton cannot be understood, by placing its components on an imaginary scale one at a time. No experiment has isolated an up quark, weighed it like a grain of rice, then done the same with the others before placing them back inside. Quark masses are inferred through theory and experimental effects. The proton itself is a unified object governed by quantum chromodynamics, the theory of quarks, gluons, and the strong interaction. The name may sound as though it involves colourful machinery, and in a technical sense it does use a property called colour charge. But the colours are labels, not actual red, green or blue light. A proton is not a tiny decorative lantern, which is probably for the best because atoms are already difficult enough to picture. Quantum chromodynamics is remarkably successful. but it is also difficult to calculate with when the strong interaction becomes truly strong. In many areas of physics, a weak effect can be treated as a small correction. One begins with a simple answer, and then adds improvements. Inside the proton, the gluons interact not only with quarks, but also with one another. This creates a dense web of activity where straightforward approximations can fail. The theory is known, the rules are known. Getting exact answers from those rules is the demanding part. Physicists therefore use several approaches. They smash particles together and study the patterns that emerge. They fire electrons at protons to probe the distribution of charge and momentum inside. They examine how quarks and gluons contribute during high-energy collisions. They also use powerful computers to simulate the strong interaction on a grid of points, an approach called lattice quantum chromodynamics. Instead of attempting to solve the full continuous problem all at once, the calculation places the theory on a discrete framework and allows the computer to estimate how quark and gluon fields behave. These calculations have reproduced the proton's mass with impressive accuracy. That achievement matters because it shows that the known theory can produce a heavy proton even when the basic quark masses are small. The mass emerges from the dynamics. It is not inserted by hand as an unexplained number. When the quark masses used in the calculation are adjusted, the proton's mass changes, but the majority remains connected to the strong interaction and the energy of the quark and gluon system. The phrase 99% is a useful way of expressing the scale of the surprise, though the exact breakdown depends on how physicists define and separate the contributions. A proton's mass cannot always be divided into perfectly independent boxes labelled quark motion, gluon energy, quark mass, and quantum effects, without some dependence on the chosen theoretical method. Different decompositions can organise the same total in different ways. What remains clear is the main lesson. The bare masses of the light quarks account for only a small part of the proton. Most of the proton's mass comes from quantum chromodynamics, from the energy and structure created by the strong interaction. This means the source of ordinary weight is more interesting than a simple collection of massive ingredients. Consider your own body. Most of its mass is in atomic nuclei. Most nuclear mass is in protons and neutrons. Most of the mass of those protons and neutrons comes from the activity of quarks and gluons. The Higgs field still matters, because without quark masses the structure and stability of matter would be different. Electrons also receive their mass through the Higgs field, and their mass is crucial for atoms and chemistry. Yet when you stand on a bathroom scale and wonder whether it has become personally judgmental, most of the number displayed is tracing back to the strong force. The same is true for mountains, oceans, books, planets, and the warm mug that seems heavier only when you're carrying several other things at once. Their mass is not mostly the direct sum of elementary particle masses. It is largely the mass of bound systems whose internal energy is locked into protons and neutrons. Matter feels solid and substantial, but much of that substance is organised energy held in stable quantum patterns. There is a temptation to say that energy turns into mass, as though one starts as energy and later changes costume. A more careful description is that mass and energy are related properties of a system. The proton has mass because of its total energy in its rest frame, including the energy of motion, fields, and interactions inside it. The gluons themselves have no rest mass, yet their fields carry energy. The quarks are light, yet their motion contributes energy. The strong interaction confines everything within the proton, creating a stable object with a definite mass. Stable does not mean motionless. A waterfall can maintain a recognizable shape while water rushes through it. A flame can remain in one place while the gases and chemical reactions within it constantly change. These comparisons are not exact, because a proton is a quantum object and not a miniature classical machine. Still, they help loosen the idea that a stable thing must be made from static parts. The proton persists while its internal quantum state remains active. Nor is the proton a hollow shell with 3 beads rattling around inside. experiments reveal distributions of charge, momentum, pressure, and internal stress. The proton has a measurable size, though its boundary is not a hard surface like the skin of a ball. The quarks and gluons are described by quantum fields spread across the region. At higher probing energies, more of the internal complexity becomes visible. The closer physicists look, the less the proton resembles a simple container, and the more it resembles an ongoing interaction. This can make the word particle slightly misleading. In daily language, a particle is a tiny speck of material. In quantum physics, a proton is a stable excitation of underlying fields with particular properties. It has charge, spin, mass, and a characteristic response to forces. It can be detected as a distinct object, but its interior does not need to look like a collection of miniature marbles. The things called quarks and gluons are themselves excitations of fields, and their interactions create the proton as a whole. The proton is also astonishingly long-lived. No confirmed proton decay has ever been observed. Some theories beyond the current standard model predict that protons may eventually decay, but if they do, their lifetime must be extraordinarily long. For all practical purposes, the protons in ordinary matter have been reliable companions since the early universe. The same strong interaction that creates most of their mass also helps make them stable enough for atoms, stars, planets, and biology to exist. This raises a deeper question. Why does the strong interaction settle into a proton with this particular mass? The theory contains a scale that emerges through quantum effects. Even if the light quarks had no basic mass at all, the strong interaction would still generate a characteristic energy scale and produce massive composite particles. This is one of the most remarkable features of quantum chromodynamics. A theory whose main force-carrying particle is massless can build objects with substantial mass through confinement and quantum dynamics. The result is not only a fact about particle physics, it is a clue about why the visible universe has the weight it does. Stars form because matter has mass and gravity gathers it. Planets hold together because atoms and nuclei provide stable material. Chemistry operates because protons define elements, and electrons arrange themselves around nuclei. Life depends on those arrangements. Beneath all of that is a strong interaction working at distances so small that no ordinary microscope could approach them. We rarely notice this hidden origin. A table does not tremble with visible gluon activity. A stone does not feel like trapped quantum motion. The world presents us with surfaces, textures, and weight, while the deeper explanation remains concealed inside each nucleus. Physics often works this way. The familiar is supported by processes that seem nothing like the experience they create. Smooth light comes from quantum events. Solid matter is mostly open space structured by fields. The steady weight of an object comes largely from restless energy inside protons and neutrons. To understand that hidden energy, we first need to become more familiar with the proton itself. We need to know what physicists mean when they say it contains quarks, why the simple picture of three components is both useful and misleading, and how experiments discovered that the proton has a structure at all. Only then can we follow the mass inward and see why the small pieces do not add up in the ordinary way. For now, it is enough to keep one quiet surprise in mind. Almost everything you can touch is heavy, mainly because particles with very little individual mass are caught inside an energetic quantum system. The weight is not sitting in one place. It belongs to the whole arrangement. Every proton carries within it a constant storm of quarks, antiquarks, and gluons, yet from the outside it behaves as one stable piece of matter. And as we move closer to that tiny object, the first thing to examine is how something so small became one of the main foundations of the visible universe. A proton is so small that even calling it tiny feels rather generous. It lives inside the nucleus of an atom, packed into a region far smaller than anything the eye could see, far smaller than the width of a human hair, and far smaller even than the wavelengths of ordinary visible light. Yet this almost unimaginably small object carries most of the mass of the simplest atom and helps provide most of the weight of nearly everything around you. The floor beneath you, the bed supporting you, the walls, the air, the trees outside, and the planet turning quietly through space all contain protons in enormous numbers. Each proton is hidden from direct view, but together they make the ordinary world feel solid, heavy, and reassuringly difficult to walk through. That's already a little strange. The things responsible for most of the weight we experience are objects we can never hold individually, never see with our eyes, and never place on a kitchen scale. A proton does not look like a grain of sand or a tiny metal ball. It is not a miniature piece of ordinary material, because ordinary material is built from things like protons. Trying to imagine what a proton is made of by picturing familiar objects is rather like trying to explain a loaf of bread using only other loaves of bread. At some point, the comparison runs out of room. The proton is found in the central nucleus of every ordinary atom. The simplest atom, hydrogen, usually contains one proton with one electron surrounding it. That proton is the nucleus. There is no collection of several nuclear particles in ordinary hydrogen. Just one proton sits at the centre, while the much lighter electron occupies the region around it. Remove the electron and the hydrogen atom becomes a positively charged hydrogen ion, which is essentially a proton on its own. Every other element contains more protons. Helium has 2, carbon has 6, oxygen has 8, iron has 26, gold has 79, uranium has 92. The number of protons determines the identity of the element. A nucleus with 6 protons is carbon, regardless of how many neutrons accompany them. A nucleus with 8 protons is oxygen. A nucleus with 79 is gold, although sadly this information does not make producing gold in the kitchen any easier. Because the proton count defines the element, protons play a central role in chemistry, even though most chemical reactions involve electrons. The arrangement of electrons around a nucleus depends on the positive charge provided by the protons. That electrical attraction shapes the structure of atoms, the bonds between them, and the molecules they form. Water behaves as water because hydrogen and oxygen atoms have particular numbers of protons, and therefore particular arrangements of electrons. Change those proton numbers and the chemistry changes completely. The proton carries 1 unit of positive electric charge. The electron carries an equal amount of negative charge. When an atom has the same number of electrons and protons, the charges cancel, and the atom is electrically neutral. This simple balance makes ordinary matter possible. If the proton carried a slightly different amount of charge from the electron, atoms might not remain neutral, and large objects could carry enormous leftover electrical forces. The fact that these charges match so precisely is one of the quiet regularities on which the familiar world depends. The proton is also massive compared with the electron. A proton has more than 1,800 times the mass of an electron. This means that although electrons fill most of the volume of an atom, they contribute only a small fraction of its total mass. The nucleus occupies a minuscule region near the centre, yet almost all the atomic mass is concentrated there. If an atom were expanded until it filled a large concert hall, the nucleus would still be extremely small compared with the room, but nearly all the mass would be found in that tiny central region. The rest would be occupied by the spread-out quantum state of the electrons, which would be excellent for seating capacity but not especially useful for supporting the roof. This concentration of mass was not always known. Early models of the atom imagined positive charge spread throughout the atomic volume, with electrons embedded inside it. One famous comparison described the atom as something like a pudding containing small pieces of fruit. It was an understandable attempt to picture an invisible structure, although physics has often advanced by discovering that nature is not as cooperative as dessert. The picture changed through experiments led by Ernest Rutherford and his colleagues in the early 20th century. they directed fast-moving, positively charged particles toward very thin sheets of gold. Most of the particles passed through with a little change in direction, suggesting that atoms were largely open space. A small number, however, were deflected sharply. A few even bounced almost backward. That result was astonishing. If the positive charge and mass had been spread evenly throughout each atom, such dramatic deflections should have been extremely unlikely. Rutherford realised that the atom must contain a tiny, dense, positively charged centre. Most incoming particles passed through the open regions, while the rare ones that came close to the centre encountered a strong electrical repulsion. The atomic nucleus had entered physics. At first, the detailed contents of that nucleus were not fully understood. Rutherford later identified the hydrogen nucleus as a fundamental positive component of other nuclei, and gave it the name proton. The word comes from a Greek term connected with being first. It was an appropriate choice. Hydrogen is the simplest element, and its nucleus appeared to be one of the basic pieces from which heavier nuclei were assembled. Later, the neutron was discovered. It carries no overall electric charge and has a mass close to that of the proton. Protons and neutrons together became known as nucleons because they inhabit the atomic nucleus. At first glance, the story now seemed tidy. Matter was made of atoms. Atoms contained electrons and nuclei. Nuclei contained protons and neutrons. It was a compact little family tree, and for a while physicists might have been forgiven for hoping that nature had finally stopped adding relatives. But the proton did not remain simple. Experiments using higher energies began to reveal that it had an internal structure. When fast particles were fired at protons, the scattering patterns showed that charge and momentum were distributed among smaller constituents. These constituents became known as quarks. The proton was no longer a final, indivisible object. It was a composite particle, built from a deeper level of quantum activity. Even before looking inside, however, the proton presents a surprising combination of properties. It is extraordinarily small, strongly massive for its size, electrically charged, and remarkably stable. It also possesses a quantum property called spin. This does not mean that the proton is literally a little sphere rotating around an axis in the ordinary mechanical sense. Quantum spin is an intrinsic property, something the proton has rather than something it performs like a spinning top. The name survives because some of its effects resemble angular momentum, even though the microscopic reality is much less familiar. The proton also behaves like a quantum object. It can show wave-like behaviour. It can exist in states described by probabilities. It does not have a perfectly hard edge or a sharply defined classical surface. Measurements of its size refer to distributions of electric charge and other internal properties. Different experimental methods can probe these distributions in different ways, and for some time measurements of the proton radius produced a puzzling disagreement. This became known as the proton radius puzzle. Measurements involving ordinary hydrogen and electron scattering gave one value, while experiments involving a heavier relative of the electron called the muon suggested a smaller result. The discrepancy led to careful new experiments and theoretical work. Over time, improved measurements brought much of the disagreement closer to resolution, although the episode served as a useful reminder that even a particle as familiar as the proton can keep experimental physicists occupied for years. The approximate size of a proton is less than 1/1,000,000,000th of a millimetre. That number is difficult to picture because human imagination was not designed for objects so small. We evolved to judge the distance to a tree, the speed of an approaching animal, or whether a piece of fruit looked worth climbing for. We did not evolve to visualize the inner scale of atomic nuclei. At that scale, comparisons become increasingly absurd. One way to approach it is to imagine enlarging a proton until it became the size of a small room. On that same enlargement, an atom would extend enormously farther. The electron cloud would not sit just outside the proton like a thin coating. It would occupy a vastly larger region. The atom is not a tightly packed solar system. It is a diffuse quantum structure with a minute nucleus at its centre. Despite its small size, the proton has a measurable mass of roughly 1.67, followed by 27 decimal places in kilograms. Written in that form, the number looks extremely small, and for a single proton it certainly is. But the proton is heavy compared with many elementary particles. In particle physics, its mass is often described using energy units, because mass and energy are deeply related. In those units, the proton has a mass energy of about 938 million electron volts. That value becomes important when compared with the masses of the proton's main quarks. The proton is commonly described as containing 2 up quarks and 1 down quark. The basic masses associated with those light quarks add up to only a small amount compared with the proton's total. Depending on how the quark masses are defined within the theory, their combined contribution is only around 1/100th of the proton's mass, give or take the details of the calculation. This is not a minor mismatch. It is not like weighing a suitcase and finding that the contents are a few grams lighter than expected. It is more like opening a heavy safe and discovering that the visible objects inside account for barely any of its weight. The proton has a large mass, but the elementary particles that determine its basic identity are themselves very light. At this point, it is natural to wonder whether something else massive is hidden inside. Perhaps there are heavier particles that have not yet been counted. Perhaps gluons, the carriers of the strong force, provide the missing rest mass. But gluons are understood to have no rest mass of their own. They still carry energy and momentum, and their role is essential, but they are not heavy little blocks placed between the quarks. The explanation requires a different way of thinking about mass. In everyday life, we often assume that the mass of an object is simply the sum of the masses of its pieces. This works well enough for furniture, luggage, groceries, and nearly everything else we encounter. A table weighs roughly as much as the wood, screws, glue, and the collection of crumbs that somehow found their way beneath it. The energy binding those parts together contributes too little to notice. For a proton, the situation is reversed. The masses of the ingredients are not the main contribution. The energy of the whole system dominates. The quarks move rapidly. Gluon fields carry energy. Quark and antiquark pairs appear temporarily through quantum processes. The strong interaction holds the entire structure together in a confined state. All of that energy contributes to what we measure as the proton's mass. This is why calling the proton a tiny object can be misleading. It is an object in the sense that it can travel, collide, and be detected as a single particle. It has a stable identity and definite overall properties, but inside it is more like a self-contained quantum environment. It is not a box holding 3 motionless quarks. It is an active state of quark and gluon fields. The familiar picture of 3 quarks is still useful, because those valence quarks determine the proton's net quantum properties. 2 up quarks and 1 down quark give the correct positive electric charge. Yet the proton also contains what physicists call a sea of temporary quark and antiquark pairs. Gluons are exchanged constantly, and because gluons themselves carry the kind of charge involved in the strong interaction, they interact with one another as well. This makes the proton's interior far more complicated than the interior of a simple mechanical object. If 3 marbles are placed in a container, the marbles remain 3 marbles. Their identities are clear, and the space between them is mostly uninteresting. Inside a proton, the fields and interactions are part of the substance of the object. The number of transient components depends on how the proton is probed and how much detail an experiment can resolve. A low-energy probe may reveal the proton as one unified particle. A higher-energy probe can reveal quarks, gluons, and increasingly fine distributions of momentum. This does not mean the proton changes its true content simply because someone looks more closely. It means that quantum systems can present different useful descriptions at different scales. A cloud seen from far away appears smooth. Seen closely it becomes droplets, currents, and turbulence. Seen closer still, it becomes molecules and atoms. The proton has its own layered descriptions, although the underlying physics is far less gentle than a cloud. The proton also lives inside nuclei, where it interacts with neighbouring protons and neutrons. Positively charged protons repel one another electrically, yet the strong nuclear interaction can hold the nucleus together over very short distances. This nuclear binding is related to the deeper strong interaction between quarks, though the effective force between protons and neutrons is often described in a different way. Some atomic nuclei are stable, others are radioactive and eventually transform. The proton itself, however, appears stable. Experiments have searched for proton decay, because several proposed theories predict that protons may not last forever. So far, no confirmed decay has been observed. The lower limits placed on the proton's lifetime are enormously longer than the current age of the universe. That stability matters more than it may first seem. If protons decayed quickly, atoms could not remain intact for long. Chemistry would lose its foundation. Planets, living cells, books, teacups, and mildly irritating alarm clocks would have no durable material from which to be made. The proton's persistence gives ordinary matter a kind of long-term reliability. Its mass also affects the universe on every scale. The mass of protons and neutrons determines much of the mass of gas clouds. Gravity draws that gas together to form stars. Inside stars, protons participate in nuclear reactions that release energy. Hydrogen nuclei combine through several stages, eventually contributing to the formation of helium and heavier elements. The sunlight reaching Earth begins with processes involving protons in the sun's interior. When a star forms, its temperature and pressure rise because a vast number of particles fall inward under gravity. The proton's mass contributes to that gravitational behaviour. The same particle that sits quietly in a glass of water also helps govern the life of stars. It is difficult to find a more successful career for something so small. Protons were also among the earlier stable ingredients of ordinary matter in the young universe. After the universe cooled enough for quarks to become confined, protons and neutrons formed. Later, some of these particles combined into the first atomic nuclei. Much later still, electrons joined nuclei to form neutral atoms. Galaxies, stars, planets, and life emerge from material whose mass was already largely contained in the strong interaction inside protons and neutrons. The question of proton mass therefore reaches back to the early universe. Why did the cosmos end up with particles carrying this particular amount of mass? Why is the proton much heavier than the quarks associated with it? Why does the strong force generate a stable object at this scale, rather than some very different one? These are not questions about an obscure laboratory detail. They concern the basic reason ordinary matter weighs what it does. There is also a delicate relationship between the proton and the neutron. The neutron is slightly heavier than the proton. That small difference has major consequences. A free neutron can decay into a proton and other particles, while a free proton cannot simply become a heavier neutron without additional energy. If the mass difference had been reversed under ordinary conditions, the structure of stable matter could have been radically different. Hydrogen depends on the proton being stable, stars depend on hydrogen, water depends on hydrogen, organic chemistry depends heavily on hydrogen. A seemingly small difference in particle masses helps shape the entire visible environment. Physics often hides enormous consequences inside very modest numerical differences, rather like a recipe in which one extra spoonful turns dinner into a small emergency. The proton's mass is measured with extraordinary precision. Physicists use devices that trap charged particles in magnetic and electric fields, allowing their motion to reveal properties such as mass and charge. Other experiments compare the proton with related particles, or study atoms whose energy levels depend subtly on nuclear properties. The result is not a vague estimate. The mass of the proton is known extremely well. Knowing the number accurately does not automatically explain where it comes from. Measurement tells us what the proton's mass is. Theory must explain why that value emerges from quarks, gluons, and the strong interaction. For many years, this was one of the most difficult challenges in particle physics, because the strong force becomes difficult to calculate at the energy scale inside protons. The theory governing that force is quantum chromodynamics. It describes quarks and gluons through a type of charge called color charge. The name color is only a label. It has nothing to do with visible color, and a proton is not glowing red, green or blue in the nucleus. The labels allow the theory to describe how quarks and gluons combine into particles with no leftover color charge. Quantum chromodynamics has a peculiar character. At extremely short distances, quarks can behave as though the interaction between them is relatively weak. At larger separations within the subatomic scale, the interaction becomes strong. Attempts to pull a quark away do not simply free it. Energy builds in the field between the quarks until the system creates new particles. This is why isolated quarks are not normally observed. The proton is therefore not assembled like a model with detachable pieces. Its quarks cannot be removed one at a time and placed on a table for inspection. Their masses and properties are inferred through the effects they produce within larger systems. The proton exists because the quarks and gluons form a confined whole. Its mass belongs to that whole. Even the word inside must be used carefully. It suggests a container with a clear boundary, an object sitting within it. Quantum fields do not arrange themselves so politely. The proton has a characteristic size, but its internal distributions fade rather than stopping at a perfectly sharp surface. What counts as the interior depends partly on what property is being measured. Physicists have studied the distribution of electric charge inside the proton, the distribution of momentum among quarks and gluons, and even quantities related to internal pressure and stress. Some analyses suggest that the pressure near the proton center is extraordinarily large, balanced by forces elsewhere that keep the proton stable. It is a compact object under intense internal conditions, yet it persists without collapsing or flying apart. This stability comes from balance. Quarks are confined by the strong interaction, but quantum mechanics prevents the system from simply settling into a motionless point. The fields carry energy. The components possess momentum. Attractive and repulsive effects combine into a stable state. The proton's mass is a measure of the total energy of that state, when the proton as a whole is at rest. From outside, a resting proton seems calm. Inside, calm is not really available. The quantum fields remain active. The proton does not need fuel to maintain this activity, because it is not a machine using up stored energy. It is a stable configuration of the fields themselves. The motion and interaction are not events happening to an otherwise separate proton. They are part of the proton's identity. This gives us the central surprise in a more precise form. The proton is not heavy, because 3 heavy quarks sit inside it. The quarks are light. The proton is heavy because an enormous amount of energy, by subatomic standards, is contained in the motion and interaction of its internal fields. The strong force creates a compact, stable state whose total energy appears from outside as mass. That is why the proton can be both tiny and unexpectedly massive. Its size does not tell us how much internal energy it contains. The same mistake would occur if we judged a storm only by the size of the cloud, without considering the speed of the winds. In the proton, however, even that comparison is too ordinary. The quarks and gluons follow quantum rules, and the force between them behaves unlike anything experienced directly in daily life. The next step is to meet those quarks more carefully. The simple statement that a proton contains 2 up quarks and 1 down quark is the doorway, not the whole room. We need to understand what quarks are, how their small individual masses are determined, why they can never be seen alone, and why adding their masses together leaves almost the entire weight of the proton unexplained. Once those like constituents come into view, the scale of the mystery becomes impossible to miss. When physicists first discovered that protons had smaller ingredients inside them, the findings seemed to offer a straightforward answer to an old question. If a proton had mass, perhaps that mass simply came from the little particles it contained. Find those particles, measure each one, Add the results together, and the proton should be explained. This is how ordinary objects behave. A loaf weighs what its flour, water, yeast, and other ingredients weigh. A suitcase weighs what the suitcase and everything packed inside it weigh. If the final number seems unusually large, there is usually a forgotten pair of shoes hiding at the bottom. The proton, however, does not follow this comfortable accounting system. Its main quarks are so light that adding their masses together barely begins to explain the weight of the particle they form. Quarks are among the smallest known building blocks of matter. As far as present experiments can tell, they have no smaller internal structure. Physicists describe them as elementary particles, meaning that they are not currently understood as objects made from other known components. That does not prove that quarks are absolutely indivisible in every possible theory, but no experiment has revealed anything inside them. When particles are elementary, their properties are treated as basic features of nature. They have particular masses, electric charges, spins, and ways of interacting, without being assembled from smaller pieces that would provide an easier mechanical explanation. There are 6 known kinds of quark. Physicists call the different kinds flavors, which is a pleasingly ordinary word for a very unusual set of particles. The 6 are known as up, down, strange, charm, top, and bottom. These names do not describe physical directions, personalities, or culinary qualities. A top quark does not sit above bottom quark, and a strange quark does not behave strangely by the standards of quantum physics, which would be a difficult competition to judge. The names are historical labels that allow physicists to distinguish particles with different masses and other properties. The up and down quarks are the lightest members of the family. They are also the quarks most important for ordinary matter. Protons and neutrons are built around combinations of up and down quarks, which means that nearly every atomic nucleus around us depends on them. The heavier quarks can appear in short-lived particles produced in high-energy collisions or in natural processes such as cosmic ray interactions. They decay quickly into lighter particles. The top quark, the heaviest of all, disappears so rapidly that it does not even have time to join with other quarks and form a long-lasting composite object. A proton is said to contain 2 up quarks and 1 down quark. This combination gives the proton its defining properties. Each up quark carries a positive electric charge equal to 2/3 of the standard unit used for particles. The down quark carries a negative charge equal to 1/3 of that unit. 2 positive contributions from the up quarks, together with the smaller negative contribution from the down quark, produce 1 complete positive charge. That is the charge measured for the proton. A neutron contains the opposite balance, with 1 up quark and 2 down quarks. The positive contribution of the up quark is cancelled by the 2 negative contributions of the down quarks, leaving the neutron with no overall electric charge. This small change in the quark arrangement turns a positively charged proton into a neutral neutron. It shows how much the identity of a composite particle can depend on the precise combination of its ingredients. The statement that a proton contains 2 up quarks and 1 down quark is one of the first facts many people learn about particle physics. It creates an appealing image of 3 tiny objects sitting together in a compact group. Perhaps they seem like 3 peas in an exceptionally small pod, or 3 marbles held inside a ball. That picture is useful only as a first step. The 3 quarks are not stationary objects resting in fixed positions. They exist within a changing quantum system filled with gluons and temporary quark pairs. The proton always has the net identity of 2 up quarks and 1 down quark, but its interior is much richer than a simple collection of 3 pieces. The 3 identity-giving quarks are usually called valence quarks. The word is borrowed from chemistry, where valence describes the capacity of atoms to form bonds through their outer electrons. In the proton, valence quarks are the quarks that determine its overall flavour and charge. They provide the permanent accounting that distinguishes a proton from a neutron or another particle. Yet they do not represent every quark-related event occurring inside the proton. Quantum fields allow energy to produce temporary pairs of quarks and antiquarks. An antiquark is the antimatter partner of a quark. It has the same mass as the corresponding quark but opposite charges. These pairs can appear and disappear within the proton as part of its internal quantum activity. They are often described collectively as the C quarks. The word C gives a more accurate feeling for the proton than the image of three beads. The interior is restless, crowded, and difficult to divide into permanent individual objects. Even the valence quarks are not always easy to identify as three particular particles travelling along clear paths. Quantum mechanics does not assign them simple little routes that could be drawn with a pencil. Instead, the proton is described through quantum states and probability distributions. Experiments can reveal how momentum, charge, and other properties are distributed among quarks and gluons, but they do not produce a photograph of three coloured balls inside a shell. The use of the word colour here introduces another important property of quarks. Quarks carry what physicists call colour charge. This has nothing to do with visible light. Up quarks are not actually red, green, or blue, and no sufficiently powerful microscope would reveal a brightly coloured interior. The colour names are labels for three forms of the charge involved in the strong interaction. They help describe how quarks combine and how gluons act between them. A proton as a whole has no net colour charge. Its internal colours combine into a colour-neutral state. This neutrality is necessary for particles such as protons and neutrons to exist freely. Individual quarks carry colour, but nature does not allow them to appear alone under ordinary conditions. They are confined inside colour-neutral combinations. Three quarks can combine in one way, while a quark and an antiquark can combine in another. These arrangements produce the families of composite particles known as baryons and mesons. Protons and neutrons are baryons because their valence structure involves three quarks. Pions and kaons are examples of mesons, whose basic valence structure involves a quark and an antiquark. The full quantum picture again includes gluons and temporary pairs, but the valence arrangement determines the particle type. This is similar to the way the number of protons identifies a chemical element, even though the atom contains other particles and interactions as well. The existence of quarks was not accepted immediately. In the middle of the 20th century, experiments were producing an increasing number of particles. Some were stable enough to study carefully, while others appeared only briefly before decaying. The list became so crowded that physicists sometimes refer to it as a particle zoo. There seemed to be too many supposedly fundamental particles, each with different charges, masses, and decay patterns. Nature looked less like an elegant system and more like a cupboard into which someone had been placing objects without labels. Murray Gell-Mann and George Zweig independently proposed that many of these particles could be understood as combinations of a smaller number of basic constituents. Gell-Mann called them quarks. The name came from a phrase in a novel by James Joyce, though the pronunciation and meaning were adapted for physics. At first, quarks were treated by some researchers as mathematical tools rather than real physical objects. They organised particle properties beautifully, but no isolated quark had ever been observed. Evidence grew through scattering experiments. Physicists directed high-energy electrons toward protons and examined how the electrons changed direction. This approach resembled Rutherford's earlier use of scattering to reveal the atomic nucleus. If a target has no internal structure, incoming particles scatter in one pattern. If it contains concentrated components, the pattern changes. The experiments showed that protons contain point-like objects carrying charge and momentum. These internal objects were first called partons because the experiments revealed parts without immediately proving exactly what those parts were. Over time, the partons were identified with quarks and gluons. The quark model changed from a useful classification scheme into a physical description, supported by extensive experimental evidence. It became part of the Standard Model, the theory describing known elementary particles and three of the fundamental interactions. Once quarks were accepted as real ingredients of the proton, the question of mass should have become easier. the proton's mass could be measured very accurately. The masses of the up and down quarks could be inferred through their effects in particle reactions and theoretical calculations. The expected procedure was simple in principle. Add the masses of 2 up quarks and 1 down quark, then compare the result with the proton. The comparison fails dramatically. The up quark has a basic mass of only a few million electron volts when expressed in the energy units common in particle physics. The down quark is slightly heavier, but it is still only a few million electron volts. 2 up quarks and 1 down quark together contribute roughly 10 million electron volts, depending on the exact definitions and values used. The proton has a mass energy close to 938 million electron volts. The difference is enormous. The basic masses of the 3 valence quarks account for only about 1% of the proton's total mass. The precise percentage varies because quark masses are subtle quantities in quantum chromodynamics, but the broad conclusion does not change. Almost all the proton's mass is missing if we look only at the elementary masses of the quarks. This can sound as though physicists have made an error in their measurements. Perhaps the quark masses are simply underestimated, yet many independent observations support the values used. The problem is not bad bookkeeping. The problem is the assumption that a proton's mass must be the simple sum of the rest masses of 3 ingredients. Quark mass itself requires care. An isolated quark cannot be removed from a proton and weighed directly because confinement prevents free quarks from existing. Physicists determine quark masses by studying how quarks influence measurable particles and reactions. The values depend partly on the energy scale and calculation method. This behavior is known as running, meaning that a particle parameter can take different effective values when examined at different scales. Running does not mean that a quark randomly changes weight like a suitcase on an unreliable airport scale. It reflects the way quantum fields surround and influence particles. At different probing energies, different layers of quantum activity become relevant. The mass parameter used in the theory must be defined in a specific way. Once that definition is chosen, calculations and experiments can be compared consistently. There is another distinction between what are sometimes called current quark masses and constituent quark masses. Current masses refer more closely to the elementary mass parameters appearing in the underlying theory. These are the small values associated with up and down quarks. Constituent masses are larger effective values used in simplified models of protons, neutrons, and other particles. They include some of the surrounding strong interaction energy, as though it travelled with each quark. A constituent quark can therefore appear to have a mass of several hundred million electron volts in certain models. 3 such effective masses can roughly match the mass of a proton. But this does not mean that the elementary quarks were secretly heavy after all. The extra mass assigned to a constituent quark is really an approximate way of packaging the energy of the surrounding gluon and quark fields. It is useful for some calculations, but it does not change the deeper conclusion that the fundamental up and down quark masses are small. This distinction reveals how strongly the identity of a quark inside a proton is shaped by its environment. In everyday objects, an ingredient usually retains nearly the same mass whether it is alone or combined with others. A screw weighs almost the same before and after it is placed into a chair. A quark cannot be treated that way. It is never found alone, and the strong field around it contributes so much to the composite particle that separating the quark from its environment becomes conceptually difficult. The Higgs field gives the up and down quarks their elementary masses. Quarks interact with the Higgs field with different strengths, and this produces the different mass values seen across the 6 flavours. The top quark interacts very strongly and is extremely massive. The up and down quarks interact weakly and are light. This is why the discovery of the Higgs boson was so important. It confirmed the mechanism responsible for the elementary masses of quarks, electrons, and several other particles. Yet the Higgs mechanism does not directly provide most of the proton's mass. This point is often lost in simplified explanations. The Higgs field explains why the up and down quarks have their small basic masses. Those masses matter greatly. Without them, the balance between protons and neutrons would change, atomic nuclei would behave differently, and the structure of matter might be altered. But they still contribute only a small portion of the proton's total. The proton's weight mainly comes from what happens after the quarks are placed under the control of the strong interaction. Their motion becomes highly energetic. Gluon fields fill the proton. Quantum fluctuations continually produce additional quark and antiquark pairs. The energy associated with all of this activity becomes part of the mass of the complete particle. It is tempting to imagine the quarks rushing around so quickly that their ordinary motion simply makes them heavier. This is partly useful but must be handled carefully. In relativity, the total energy of moving particles contributes to the mass of a closed system. However, the internal motion of quarks is not classical motion along well-defined tracks. It is quantum behavior described by fields and probability amplitudes. The phrase motion energy gives an accessible starting point, but the complete explanation belongs to quantum chromodynamics. The uncertainty principle also plays a role in understanding why quarks cannot sit quietly inside such a small region. Confining a quantum particle to a tiny space means that its momentum cannot be precisely small. A tightly confined quark must have a broad range of possible momentum, which is associated with significant energy. The proton's small size therefore helps ensure that its constituents remain highly active. One might wonder whether this energy should make the proton unstable. If the interior is so energetic, why does it not burst apart? The answer is that there is no lower energy arrangement in which the quarks simply fly away as isolated particles. Confinement prevents that outcome. Pulling quarks apart adds energy to the strong field rather than releasing them. Given enough energy, new quark and antiquark pairs can form, producing new composite particles, but a lone quark does not emerge. The proton is therefore a stable pattern within the strong interaction. Its energy is not like steam trapped in a container that will eventually force the lid off. The fields, the quarks, and the confinement together form the object. The energy is part of the structure rather than something accidentally stored inside it. The small quark masses still influence the proton in important ways. They contribute directly to its total mass, though only modestly. They also affect the surrounding quantum fields. Changing the up and down quark masses in theoretical calculations changes the mass of the proton and the behavior of other particles. Lattice quantum chromodynamics allows physicists to explore these relationships by simulating the theory under different conditions. The proton would remain massive even if the up and down quark masses were reduced towards zero. Its exact properties would change, but the strong interaction would still generate a large characteristic scale. This is one of the deepest clues in the puzzle. Most of the proton's mass does not need heavy elementary ingredients. It can arise dynamically from a theory built around nearly massless quarks and massless gluons. The word dynamically means that the mass emerges from activity and interaction. It is not placed into the proton as a fixed collection of heavy parts. It appears because the fields behave in a particular way. The strong interaction creates its own energy scale through quantum effects, and that scale determines much of the mass of protons, neutrons, and related particles. This behavior separates ordinary visible matter from some other forms of mass in the standard model. An electron is elementary and does not contain quarks or gluons. Its mass comes directly through its interaction with the Higgs field. A proton is composite, and most of its mass arises from strong interaction energy. Both objects have mass, but the physical origins are different. If the visible universe consisted mainly of electrons, the Higgs field would account directly for much more of its mass. Instead, ordinary matter contains heavy nuclei made from protons and neutrons. Electrons are essential for atoms and chemistry, but their contribution to total weight is small. The scale on a bathroom floor is responding mainly to mass created by quantum chromodynamics, although it remains unlikely to display a helpful message explaining this. The quarks also contribute to the proton's spin, but once again they do not provide the whole answer in the simplest way. Early physicists expected the spins of the three valence quarks to add up to the proton's measured spin. Experiments showed that quark spins account for only part of it. Gluon spin and the orbital motion of quarks and gluons also contribute. This became known as the proton spin puzzle. The mass puzzle and spin puzzle are related in spirit. Both show that a proton cannot be understood by treating it as three independent quarks placed side by side. Its properties belong to the collective quantum system. The quarks matter enormously, but their behavior is inseparable from the gluon fields and from the complex internal motion produced by the strong interaction. Even the distribution of momentum inside a fast-moving proton reveals this collective structure. Experiments show that quarks carry part of the proton's momentum, and gluons carry a large part as well. At high energies, the proton appears filled with increasing numbers of low-momentum gluons and C-quarks. The internal picture depends on the resolution of the probe, but it is never reduced to three quiet constituents. The valence quarks remain essential because they define what the proton is. Remove the net pattern of two up quarks and one down quark, and the particle is no longer a proton. Yet those same quarks contribute surprisingly little through their elementary masses. Their greatest role in the proton's weight comes indirectly, through the energetic state they form with the gluons. This is why the small pieces barely explain the mass when considered alone. They explain the charge, they explain the flavour, they help explain the particle's identity. They provide the ingredients on which the strong interaction acts. But the weight belongs mainly to the activity that develops between and around them. A quiet proton resting in a laboratory detector contains quarks that cannot rest in the ordinary sense. They are confined to a tiny region, exchanging gluons, surrounded by fluctuating pairs and participating in a strongly coupled quantum field. From outside, this entire arrangement appears as one stable particle with a well-defined mass. From inside, the mass is distributed across motion, fields, and interaction, rather than concentrated in the quark masses themselves. The next part of the explanation belongs to the gluons. They have no rest mass, yet they carry energy. They bind quarks while also interacting with one another. They fill the proton with a complicated field that refuses to weaken when quarks are pulled apart. To understand how massless force carriers help create nearly all the weight of ordinary matter, we have to follow the strong force into the space between the quarks, where the apparently empty region turns out to be the busiest part of the proton. The space between quarks may sound like the least interesting part of a proton. If three small particles are packed into one tiny object, it is natural to imagine that the quarks are the important pieces and everything between them is merely empty room. In everyday life, the space between objects usually contributes very little. The air between books does not hold the shelf together. The gap between the legs of a table does not explain why the table has weight. Inside a proton, however, the apparent space between the quarks is filled with the activity that makes the whole structure possible. It is occupied by gluon fields, constant exchanges of energy and momentum, and a strong interaction so intense that it accounts for much of the proton's surprising mass. Gluons are the carriers of the strong force. Their name comes from the idea that they glue quarks together, which is useful as long as we do not take the comparison too literally. A gluon is not a sticky substance spread between solid particles. It is an elementary quantum particle associated with the field that produces the strong interaction. Quarks respond to this field because they carry colour charge, and gluons transmit changes in that charge from one part of the system to another. Other forces in nature also have carrier particles. The electromagnetic interaction is associated with photons. Light itself is made from photons, and electromagnetic forces between charged particles can be described through the photon field. The weak interaction is carried by particles known as the weak bosons. Gravity may have a quantum carrier called the graviton, though no graviton has been detected and a complete quantum theory of gravity remains unfinished. The gluon fills a similar role for the strong interaction, but it comes with an important complication. Gluons carry the very charge to which they respond. Photons do not carry electric charge. Two photons can pass through one another without directly producing the same kind of interaction that charged particles experience. Gluons are different because they carry color charge. A gluon can therefore interact with another gluon. This single feature makes the strong force much more complicated than electromagnetism. The force carriers are not merely delivering messages between quarks, they're also exchanging messages among themselves, responding to the field while helping create it. The result is a dense, self-interacting system. A quark emits a gluon, changing its color charge. That gluon may interact with another gluon, which may influence another quark, while additional quantum fluctuations occur throughout the proton. No single exchange can be isolated as the permanent thread holding the particle together. The proton exists as a complete state of interacting quark and gluon fields. Physicists use 3 color labels for quarks, usually called red, green and blue. Antiquarks carry corresponding anticolors. Once again, these labels are not visible colors. They are names for different forms of strong charge. A proton combines its internal colors in such a way that the particle as a whole is color neutral. This is sometimes compared with the way red, green and blue light can combine to produce white, though the resemblance is only a naming convenience. Gluons carry combinations of color and anticolor. As they move between quarks, they can change one color into another while preserving the overall balance. A quark labeled red might emit a gluon and become blue. Another quark can absorb that gluon and change accordingly. The individual labels continually shift, but the proton remains color neutral as a whole. If this sounds like an elaborate system for keeping track of labels, that is because the real mathematics is doing something highly precise beneath the simple language. Color charge determines which interactions are allowed, how strongly fields respond, and how quarks can combine into observable particles. The rule of color neutrality explains why protons and neutrons can exist freely, while isolated quarks cannot. There are 8 independent types of gluon in the theory. This number arises from the possible combinations of color charge after one redundant neutral combination is removed. The details require mathematics that we can leave resting quietly in the next room. What matters here is that the strong field is not carried by one simple kind of messenger. It has several connected states, each capable of interacting with quarks and with other gluons. Gluons have no rest mass. If a gluon could be isolated and examined as a free particle, it would behave as a massless object, travelling at the speed of light. Yet gluons are never found travelling freely across ordinary space in the way photons do. They remain confined within particles such as protons, neutrons, and other combinations of quarks. The idea that massless gluons help create a massive proton may seem contradictory. If the force carriers have no rest mass, and the light quarks contribute very little, where can the weight come from? The answer is that an object does not need to be made from massive parts in order to have mass as a complete system. The energy carried by massless particles can contribute to the mass of a confined object. Imagine a perfectly sealed mirrored box containing light. Photons have no rest mass, but the light has energy and momentum. The box containing that trapped light would have slightly more mass than the same box without it. The difference would be extremely small in an ordinary experiment, but it would be real. The energy inside the system contributes to the total mass measured from outside. A proton is not literally a mirrored box of gluons, but the general lesson applies. Gluons carry energy and momentum within the confined proton. They cannot simply escape. Their fields are part of a stable quantum structure, and the energy of that structure contributes to the proton's mass. The gluons do not need rest mass of their own to help produce a massive composite object. The strong force also behaves differently, with distance from forces we meet in ordinary life. Electric attraction becomes weaker as charged objects move farther apart. Gravity also weakens with distance. If the Sun suddenly moved much farther from Earth, its gravitational pull on our planet would decrease. This is familiar behaviour. Separation usually means a weaker connection. Between quarks, the strong interaction does not fade in the same simple way. When quarks are very close together, they can behave almost as though they are weakly interacting. This property is called asymptotic freedom. At extremely short distances or very high energies, the quarks become relatively free to move. The closer physicists probe, the more the interaction appears to relax. As the distance grows, the interaction strengthens. Pulling two quarks apart requires increasing energy. The gluon field becomes concentrated between them, often pictured as a narrow tube of strong field. This resembles stretching an elastic cord, although the real quantum behavior is more complex. The farther the quarks are separated, the more energy is stored in the field. Eventually, adding enough energy does not release an isolated quark. Instead, the energy can create a new quark and antiquark pair. The original system breaks into new color neutral particles. It is as though the stretched cord does not snap into two loose ends, but produces two complete cords. Nature avoids leaving a bare color charge exposed. This behavior is called confinement. It is the reason quarks and gluons are never normally observed alone. Particle accelerators can strike protons with enormous energy and disrupt their internal arrangement, but the quarks do not fly into detectors as isolated particles. They rapidly form new combinations, producing streams of hadrons known as jets. Scientists infer the presence of quarks and gluons from the direction, energy, and types of particles in these jets. Confinement means that the gluon field is not an optional addition to the proton. It cannot be removed while leaving the quarks sitting together in a quieter state. Without the strong field, the proton would not exist. The binding, motion, and quantum fluctuations created by gluons are part of the particle's basic structure. The word binding may create another possible misunderstanding. In many everyday systems, binding energy makes the finished object slightly lighter than its separated pieces. An atomic nucleus has less mass than the total mass of the free protons and neutrons from which it is assembled. Energy is released when the nucleus forms, leaving the bound system with less total energy and therefore less mass. This difference is known as a mass defect. The proton is not directly comparable, because its quarks cannot exist as free particles that could be weighed before assembly. There is no practical starting collection of three isolated quarks whose masses can be added and then reduced by binding. The confined system is the only observable form. The small elementary quark masses are parameters in the theory, while the proton's much larger mass emerges from the entire strong interaction. In simplified language, gluons hold the quarks together. In a deeper description, quarks and gluons form a self-consistent quantum state. The gluon fields create the confinement, while the confined quarks influence the gluon fields. Neither side simply acts on the other from outside. The proton is the combined result. Gluons also produce temporary quark and antiquark pairs. A gluon carrying sufficient energy can briefly become such a pair, and the pair can later recombine into gluons. These processes occur as quantum fluctuations inside the proton. They contribute to the sea of quarks surrounding the valence structure. Some of these sea quarks are up and down quarks. Others can involve heavier flavors, particularly strange quarks for brief periods. The heavier the pair, the more energy is required, so the probabilities differ. None of these temporary pairs changes the proton's net identity. Every added quark appears with a matching antiquark, leaving the overall valence balance of two up quarks and one down quark unchanged. This internal sea is not a collection of particles appearing according to a hidden clock. Quantum fluctuations are part of the mathematical state of the proton. Depending on how the proton is probed, different arrangements contribute to the measured outcome. The language of particles appearing and disappearing is useful, but it should not be mistaken for a tiny cinema playing inside the nucleus. Experiments reveal that gluons carry a substantial portion of a proton's momentum when the proton moves rapidly. The exact distribution depends on the energy and resolution of the measurement. At higher energies, The proton appears to contain very large numbers of gluons carrying small portions of the total momentum. The closer physicists look, the more crowded the internal picture becomes. This does not mean that the proton has a fixed hidden number of gluons that scientists have simply not counted yet. In quantum field theory, the number of particles can depend on the state of motion and the way the system is examined. What remains consistent are the measurable predictions of the full theory. The gluon field also contributes to the internal pressure of the proton. Modern experiments and theoretical calculations have begun mapping how forces are distributed within it. Near the centre, there appears to be an enormous outward pressure, while outer regions provide balancing inward forces. These pressures are far greater than anything encountered in ordinary materials. The proton does not explode because the stresses balance in a stable quantum state. The outward tendencies associated with quark motion and internal pressure are countered by the confining effect of the strong field. The particle maintains a characteristic size because expanding or contracting it would change the energy of the system. A helpful comparison is a musical instrument string, though only as a loose guide. A string has tension, and its allowed vibrations depend on its length and boundaries. The energy of the vibration belongs to the full string rather than to one chosen point. Inside a proton, the quark and gluon fields have allowed quantum states shaped by confinement. The proton's mass reflects the energy of its lowest stable state. Unlike a string, however, the gluon field interacts with itself. The instrument would be more peculiar if every vibration altered the material of the string, created new temporary strings, and changed the rules governing the next vibration. This gives some sense of why calculations involving the strong interaction become difficult at proton scales. The theory of gluons and quarks is called quantum chromodynamics. The word chromodynamics refers to the behavior of color charge. It belongs to the Standard Model and has survived a wide range of experimental tests. At high energies, where the strong interaction becomes weaker, physicists can calculate processes using systematic approximations with impressive precision. At the lower energies characteristic of a proton's interior, the interaction becomes strong enough that these ordinary approximation methods stop working well. Each added correction can be as important as the one before it. It is like trying to estimate the behavior of a crowded room by first considering one conversation, then adding a second, only to discover that everyone is speaking to everyone else and rearranging the furniture. To handle this region, scientists often use lattice quantum chromodynamics. In this method, space and time are represented by a grid of discrete points. Quark and gluon fields are placed on this grid, and powerful computers calculate the possible configurations. By making the grid finer and the simulated region large enough, physicists can approach the predictions of the continuous theory. These calculations are demanding. The number of possible field arrangements is enormous, and accurately representing light quarks requires substantial computing power. Decades of improvements in algorithms and machines have made it possible to calculate the masses of protons, neutrons, and many other particles from the underlying theory. The results show that gluon dynamics and quark motion can generate the observed proton mass. When physicists provide the basic parameters of quantum chromodynamics, including the small masses of the light quarks, the simulated proton emerges with a mass close to the measured value. This is a major success because the large number is not placed into the calculation as the proton's known answer. It develops from the behavior of the fields. Gluons contribute in more than one way. Their electric and magnetic color fields store energy. Their self-interactions help establish the characteristic scale of the strong force. They transfer momentum among quarks and participate in the quantum fluctuations filling the proton. Separating these contributions into exact percentages is not always straightforward, because the terms can depend on the theoretical method used. This is why simple statements such as gluons provide a certain fixed portion of the proton's mass should be treated cautiously. Quark energy, gluon energy, the small direct quark mass contribution, and quantum effects are intertwined. Physicists can define careful decompositions, but the boundaries between categories are not as natural as dividing groceries into separate bags. The safe conclusion is that the strong interaction provides almost all the proton's mass, and gluons are central to that interaction. They create and carry the fields in which quarks are confined. Their energy forms a large part of the total energy of the proton. Their self-interaction gives quantum chromodynamics the distinctive behaviour that allows massive hadrons to emerge from light quarks and massless force carriers. The gluon's lack of rest mass is itself essential. A massless carrier can support a long-range field in principle, but confinement prevents the colour force from appearing across large everyday distances. Colour-neutral particles do not produce a simple external colour field, like the electric field surrounding a charged object. The strong force remains largely hidden within hadrons. A residual version of the strong interaction does extend between protons and neutrons inside atomic nuclei. This nuclear force can be understood as an effect left over from the deeper quark and gluon interaction, somewhat as neutral molecules can still attract one another through uneven electrical effects. The residual strong force binds many nuclei together despite the electrical repulsion between positively charged protons. The gluons themselves remain inside the nucleons. They do not travel directly from one nucleus to another over ordinary distances. Effective particles such as pions help describe the nuclear force between protons and neutrons. The distinction is important because the force binding a quark inside a proton and the force binding protons inside a nucleus are related but not identical descriptions. The energy associated with nuclear binding changes the mass of an atom slightly. Nuclear reactions can release some of this energy, as occurs in stars and nuclear power. Yet this is a much smaller mass effect than the one already present inside each proton and neutron. Before nuclei form, quantum chromodynamics has already generated most of their mass. The Sun offers a useful example. Its light and heat come from nuclear fusion, in which hydrogen nuclei eventually become helium. The final helium nucleus has slightly less mass than the original particles, and the difference leaves as energy. But the vast majority of the original proton mass does not disappear. It remains in the protons and neutrons of the new nucleus, because the strong interaction continues operating inside them. Every beam of sunlight is therefore connected indirectly to the mass stored in nuclear systems, while every proton involved already carries a much larger store of strong interaction energy in its internal quark and gluon structure. Nature builds energy relationships inside energy relationships, with each scale offering its own useful description. The proton has existed in something close to its current form since the young universe cooled enough for quarks and gluons to become confined. Earlier, the universe was so hot and dense that matter existed in a state called quark-gluon plasma. In that environment, quarks and gluons were not locked into individual protons and neutrons in the usual way. They moved through a larger, strongly interacting medium. As the universe expanded and cooled, quarks and gluons became confined into hadrons. Protons and neutrons emerged as stable or nearly stable combinations. At that moment, much of the mass structure familiar today appeared. The elementary quarks remained light, but the energy of confinement produced much heavier composite particles. Scientists recreate quark-gluon plasma for extremely short periods in high-energy collisions between heavy atomic nuclei. These experiments do not simply melt protons into a gas of independent particles. The resulting matter behaves more like a nearly perfect fluid with strong collective motion. Even when confinement is disrupted, quarks and gluons remain strongly connected. This is another reminder that the strong force earns its name. At ordinary proton scales, it binds quarks so completely that none escapes alone. At extreme temperatures, it produces a fluid whose components interact intensely. Gluons are present throughout both descriptions, carrying colour and shaping the collective behaviour. Without gluons, protons would not exist. Without protons and neutrons, atomic nuclei would not exist. Without nuclei, atoms and chemistry would have no foundation. The invisible gluon field inside matter is therefore not an obscure detail added after the world was built. It is one of the reasons there is a stable material world to describe. A wooden table appears motionless, but each proton in the wood contains gluon fields, changing on timescales far shorter than anything our senses can follow. A mountain looks permanent, but its weight comes largely from countless confined systems of massless gluons and light quarks. The contrast between the quiet surface and the active interior is enormous. Still, saying that gluons hold everything together is only part of the explanation for mass. The field stores energy, but so does the motion forced upon the quarks by confinement. A particle restricted to the tiny volume of a proton cannot remain still. Quantum mechanics gives it substantial momentum, and relativity makes that momentum an important part of the system's total energy. The proton's weight therefore comes not from one hidden ingredient but from a balance of activity. Gluon fields pull and reshape. Quarks move within the confinement. Temporary pairs add to the quantum sea. Internal pressures settle into a stable arrangement. From the outside, all of this is measured as the mass of one proton. To follow the missing weight more closely, we now need to look at that motion and ask how energy inside a resting object can make the object massive. The proton may sit still on a laboratory table, but none of its internal ingredients shares that stillness. The distinction between the motion of the whole particle and the motion within it is where the next part of the answer begins. A proton can be completely still, and yet contain almost nothing that could honestly be called stillness. Place a proton in a laboratory, arrange the experiment so that the particle as a whole has no motion relative to the detector, and its measured position may remain in one region. From the outside, it is at rest. Inside, however, the quarks and gluon fields remain intensely active. Momentum moves through the system. Energy is stored in changing fields. Quantum fluctuations continually reshape the internal state. The proton does not become quiet merely because it has stopped travelling across the room. Its external motion has ended, but its internal activity is part of what the proton is. This distinction between the motion of an object and the motion within it is familiar in ordinary life. A closed box can rest on a table while a small fan spins inside. A cup of hot tea can sit motionless while its molecules move rapidly in every direction. A parked car can contain a running engine, although leaving it that way for too long may lead to questions from the neighbours. The object as a whole can remain still, even while energy circulates within it. When the contents of an ordinary object become more energetic, the total mass of the object increases. Heating a cup of tea adds energy to the motion of its molecules, so the hot tea has slightly more mass than the same tea after it cools. Winding a spring stores energy, which means the wound spring is very slightly more massive than the relaxed spring. Charging a battery increases its stored energy, and therefore increases its mass by a tiny amount. These differences are far too small for a normal household scale to notice. The extra mass of hot tea would not rescue anyone from the suspicion that the biscuit was responsible for the afternoon weight gain, yet the principle is real. Energy stored inside a system contributes to the mass of that system. Inside a proton, the internal energy is not a tiny correction, it is the main contribution. The proton is almost the reverse of an ordinary object. A table receives nearly all its mass from the particles making up the wood, while the energy of the chemical bonds and molecular motion changes the total only slightly. The proton receives only a small fraction of its mass from the basic masses of its quarks. The motion and interaction energy inside it provide most of the rest. This is one reason the familiar distinction between mass and energy can become misleading. They are not unrelated quantities belonging to separate worlds. Mass is one way the total energy of a closed system appears when the system is viewed at rest. The proton has a definite rest mass, because it possesses a definite total energy in its own resting frame. That energy includes the elementary masses of the quarks, but it also includes their momentum, the energy in the gluon fields, and the effects of the strong interaction. There is no need to write an equation to understand the central point. Energy has weight in the broad physical sense. A system containing more energy is harder to accelerate than the same system containing less. It also responds to gravity as a system with greater mass. The energy does not need to be shaped like a solid ingredient. Motion, pressure, radiation, and fields can all contribute. Imagine a perfectly sealed container with light bouncing between mirrored walls. Light has no rest mass. A photon cannot be brought to rest and weighed like a pebble. But the photons carry energy and momentum. As they strike the walls, they exert pressure. The closed container filled with light has more mass than the empty container. From outside, the trapped energy behaves as part of the complete object. Now imagine that the container is removed and the trapped energy itself forms a stable, self-confined quantum system. This is still not an exact picture of a proton, but it comes closer to the important idea. The proton is not a rigid box holding energy supplied from elsewhere. The quark and gluon fields create the boundaries, the contents, and the confinement together. The energy is not added to a pre-existing proton. The organized energy is the proton. The quarks inside this system are extremely light when their basic masses are considered, yet they cannot sit motionless. Quantum mechanics prevents a particle confined to a very small region from having a perfectly definite and tiny momentum. The more tightly its position is restricted, the broader the range of possible momentum becomes. This is part of the uncertainty principle. The uncertainty principle is sometimes described as a problem caused by measurement, as though quarks would know exactly where they were and how they were moving if only physicists would stop bothering them. The deeper meaning is different. A quantum state simply cannot possess an exactly defined position and an exactly defined momentum at the same time. This limitation belongs to the structure of quantum theory, not to the clumsiness of laboratory equipment. A proton confines its quarks to a region much smaller than an atom. Because the allowed space is so small, the quarks possess substantial momentum. They do not trace neat circular orbits, and it would be misleading to assign each one a clear speed along a fixed route. Their motion is represented through quantum states and momentum distributions. Even so, the important physical conclusion remains. Tight confinement produces a large amount of internal kinetic energy. In an ordinary mechanical system, kinetic energy is the energy associated with motion. A rolling ball has more kinetic energy when it moves faster. A speeding train is harder to stop than one moving slowly. Inside the proton, the idea survives, but must be expressed through relativistic quantum mechanics. The quarks are so light and so energetic that their behavior cannot be treated with the simple rules used for slow-moving objects. A light quark inside a proton carries momentum far larger than might be expected from its tiny basic mass. It behaves in a highly relativistic way, meaning that its motion energy is extremely important. The quark is not merely a small mass travelling around. Much of its energy comes from momentum rather than from its elementary mass. This is one of the first major sources of the proton's missing weight. The up and down quarks contribute little through their basic masses, but the energy associated with their confinement and momentum is large. They barely explain the proton when counted as resting ingredients, yet they contribute much more when their full quantum motion is included. The gluons add another large contribution. Their colour electric and colour magnetic fields store energy throughout the proton. These names are borrowed from electromagnetism because the fields share some structural similarities with electric and magnetic fields. They are not ordinary electricity or magnetism, however. They belong to colour charge and the strong interaction. A field can carry energy even when its carrier particle has no rest mass. The electromagnetic field carries energy in sunlight, radio waves, and the pressure of light. In a proton, gluon fields carry energy while also interacting with themselves. Their activity helps confine the quarks, transfers momentum, and produces much of the internal structure that gives the proton its mass. It is tempting to ask how much of the proton comes from quark motion and how much comes from gluon energy. Physicists do study this question, but the answer is not as simple as dividing a cake into neat slices. In quantum chromodynamics, the different contributions are linked. The value assigned to one part can depend on the theoretical definitions and the scale at which the proton is examined. A calculation may separate direct quark mass, quark energy, gluon field energy, and a quantum contribution related to the structure of the theory. Another calculation may organize the same total differently. The complete proton mass is unambiguous and measurable. The individual accounting categories require careful definitions. This does not mean the explanation is uncertain or merely a matter of opinion. Different ways of dividing a household budget can still agree on the total amount spent. One person may place the electricity used by the oven under food costs, while another places it under utilities. The categories differ, but the missing money has not vanished. In the proton, the precise bookkeeping can vary, while the central conclusion remains firm. The small elementary quark masses account for little. Strong interaction energy accounts for most of the total. The phrase mass created inside the proton should also be handled carefully. The proton is not continually manufacturing new mass as time passes. Its mass does not grow because the quarks keep moving. A stable proton maintains a stable total energy. The motion and fields contribute to that fixed value. Created here means generated by the dynamics of the system. If the strong interaction did not confine the quarks and produce its own energy scale, the large proton mass would not appear. The mass emerges from the way the fields organize themselves. It is a property of the stable state rather than a substance being produced second by second. A simple comparison can be made with sound in a musical instrument. A guitar string has allowed patterns of vibration determined by its length, tension, and material. The lowest note is not inserted into the string as a separate object. It emerges from the structure and behavior of the complete system. Change the tension, and the allowed note changes. The proton is vastly more complicated, but its mass also resembles an allowed energy state. Quark and gluon fields confined by the strong interaction settle into a lower stable arrangement with specific properties. The energy of that arrangement determines the proton mass. Excite the system, and it can form a heavier particle, just as a string can support higher modes of vibration. Particle accelerators regularly produce excited relatives of the proton. These heavier states contain similar quark structures but possess additional internal energy. They are unstable and quickly decay into lighter particles. Their extra mass is another demonstration that internal energy changes the mass of a composite system. The ordinary proton is the lightest stable baryon with its particular conserved properties. It cannot simply release part of its internal energy and remain a smaller, lighter proton, because no lower proton state exists. The energy is not excess heat waiting to escape. It is the minimum energy required for that confined quantum object to exist. This helps explain why the quarks cannot slow down until the proton loses most of its mass. There is no quiet version hidden beneath the active one. If the internal energy were fundamentally removed, the field configuration would no longer describe a proton. Asking what remains after removing the motion and gluon energy is like asking what remains of a wave after removing its shape and movement. The defining structure has been taken away. The proton also contains pressure. Quark motion creates an outward tendency, while gluon interactions and confinement provide balancing effects. The internal stresses are enormous by everyday standards, yet the proton remains stable because the pressures balance across its structure. Pressure itself contributes to the energy relationships described by relativity. In a relativistic system, energy density, momentum flow, and pressure are deeply connected. The proton is not merely a lump containing a certain amount of energy. It has a detailed internal arrangement of stresses that determines its size and stability. Modern experiments have begun revealing these internal pressure distributions by studying processes involving high-energy particles. Physicists cannot insert a microscopic pressure sensor into a proton. Instead, they measure scattering patterns and use quantum theory to reconstruct information about how momentum and forces are distributed. The results suggest a region of intense outward pressure near the centre, balanced by inward pressure farther out. The exact interpretation requires care, but the broad image is of a stable particle held in a delicate balance between competing internal tendencies. The proton does not behave like a hard bead. It behaves like a compact quantum system under stress. The energy density inside a proton is extraordinary. Most of the proton's mass energy is concentrated within an extremely small volume. If ordinary matter could somehow be compressed to similar conditions without changing its physics, the result would be unlike any material encountered in daily life. But this comparison must be kept loose because a proton is not a tiny piece of bulk matter. Density in the usual sense does not capture the full behaviour of quantum fields. Still, the concentration explains why such small particles can provide so much of the mass around us. A single proton is almost unimaginably light by human standards, but matter contains enormous numbers of them. A modest object contains more protons and neutrons than ordinary language can comfortably describe. The mass generated inside each one adds together to produce the weight we know. When you lift a book, your muscles are working against inertia and gravity, associated mainly with proton and neutron mass. That mass comes mainly from quark momentum and strong fields. The resistance felt in your hand is therefore connected to confined quantum activity occurring inside every atomic nucleus in the pages. Nothing about the book's appearance suggests this. It looks calm. Its atoms remain in place. The printed words do not shimmer with visible gluons, yet almost all its weight comes from particles whose internal constituents are moving and interacting with tremendous energy. The contrast becomes even more striking when compared with the Higgs field. The Higgs mechanism gives basic mass to elementary particles such as quarks and electrons. This is a fundamental part of the Standard Model. Without it, the universe would be radically different. But the Higgs field is not directly responsible for most of the mass of the book. It provides the small elementary masses of the up and down quarks. Quantum chromodynamics then takes those light quarks and massless gluons and produces protons and neutrons nearly 100 times heavier than the direct quark mass contribution would suggest. The Higgs field therefore sets important ingredients, while the strong interaction performs most of the mass building for ordinary visible matter. Neither story replaces the other. They operate at different levels. The Higgs explains why elementary particles have their basic masses. Quantum chromodynamics explains why composite nuclear particles are much heavier. Even if the light quark masses were removed in a theoretical version of nature, protons and neutrons would not become massless. Their exact masses and the balance between them would change, but strong interaction energy would remain. The proton would still possess a mass generated dynamically by confinement. This fact is one of the most remarkable outcomes of modern particle physics. A theory containing nearly massless quarks and exactly massless gluons can produce a stable particle with a substantial mass. The scale appears through quantum effects in the strong interaction itself. At first, this may seem to move the question rather than answer it. If the quarks do not provide the mass and the gluons have no rest mass, perhaps saying that energy provides it is merely giving the mystery a different name. But the statement has precise physical content. The energy can be calculated from the theory. It affects momentum, scattering, pressure, and the measured mass of the proton. It is not a vague hidden force. The difficult part is that the strong interaction cannot be calculated easily at proton scales using the simplest methods. At high energies, quarks and gluons interact weakly enough for physicists to begin with an approximate answer and add small corrections. At lower energies, the corrections are no longer small. The fields interact strongly, and every part influences the rest. The proton sits in this difficult region. Its mass emerges where quantum chromodynamics is most complicated. Understanding it requires methods capable of handling strong coupling, self-interacting gluons, confinement, and the constant creation of virtual quark pairs. This is why the explanation took decades to develop fully. Physicists knew the underlying theory, but extracting the proton mass from it demanded new, computational techniques and increasingly powerful machines. The rules were available, yet following all their consequences was rather like knowing the rules of chess and being asked to predict every possible game at once. One of the most successful approaches places quantum chromodynamics on a grid. Space and time are represented by closely spaced points, and the quark and gluon fields are calculated across this lattice. Computers sample vast numbers of possible arrangements and determine which ones contribute most strongly to the proton state. As the grid becomes finer and the simulation becomes more realistic, the calculation approaches the continuous physical world. The proton mass that emerges agrees closely with experiments. The internal motion and field energy are sufficient. No unknown massive ingredient is needed. The agreement is important because it transforms the explanation from a suggestive idea into a quantitative success. Physicists are not merely saying that the proton feels energetic inside and therefore must be heavy. They begin with quantum chromodynamics, include the measured quark masses, simulate the fields, and obtain the masses of protons, neutrons, and many related particles. The same theory explains patterns across a wide family of hadrons. Change the quark combination and the resulting mass changes. Replace a light quark with a heavier strange charm or bottom quark, and the balance between elementary mass and strong interaction energy shifts. The predictions match a broad range of observed particles. For light quarks, the generated energy dominates. For very heavy quarks, the basic quark mass becomes a much larger part of the composite particle. A particle containing a bottom quark or charm quark carries significant mass directly from the Higgs-related mass of that heavy quark. The proton, built from the lightest quarks, provides the clearest example of mass emerging mainly from dynamics. Motion is therefore central, but it cannot be separated from confinement. The quarks carry large momentum because they are restricted to a tiny region. The gluon field creates that restriction. The field itself carries energy because of the color charges and self-interactions. Quantum fluctuations add further activity. Every piece of the explanation supports the others. Remove confinement and the quark momentum distribution changes. Remove gluon self-interaction, and the strong force loses the behavior needed to create the same proton. Remove the light quarks and there is no valence structure defining the particle. The mass belongs to the complete arrangement. This collective origin is why a proton cannot be understood through the same intuition used for a bag of groceries. The contents do not exist independently in the same form outside the bag. The container is made from the interaction of the contents. The energy holding the structure together provides most of the weight. Opening the bag does not reveal 3 items resting politely at the bottom. Perhaps the closest everyday lesson is that an object can be more than the sum of its separately imagined parts. In ordinary language, that phrase usually refers to teamwork, music, or a meal that turned out surprisingly well. In the proton, it is a literal statement about mass. The elementary masses add to only a small fraction. The quantum system contributes the rest. The weight of ordinary matter is therefore not mainly a record of how strongly its smallest particles interact with the Higgs field. It is a record of how energy behaves when color-charged quarks and gluons are confined. The stable mass of the proton is the external signature of an internal quantum balance. To understand why that balance has its particular rules, we need to look more directly at quantum chromodynamics. The theory explains why quarks become nearly free at very short distances, why the interaction grows stronger when they separate, why gluons interact with one another, and why a characteristic mass scale appears even when the original particles are almost massless. The motion and energy inside the proton have brought us to the answer in physical terms, but the next step is to examine the rulebook that makes such an unusual object possible. Quantum chromodynamics is the theory that explains how quarks and gluons behave. The name sounds complicated, but each part of it has a simple purpose. Quantum tells us that the theory follows the rules of quantum physics. Chromo refers to color charge, the the special kind of charge carried by quarks and gluons. Dynamics means that the theory describes how those particles move, interact, exchange energy, and form larger objects. Put together, quantum chromodynamics is the rulebook for the strong interaction, the force that binds quarks inside protons, neutrons, and many other particles. The theory is often shortened to its initials when physicists discuss it, but we will keep using its full name for a while because the words remind us what the theory is actually doing. It is not a theory about visible colour. It is not concerned with why the sky looks blue, or why a cup appears red. Colour charge is simply a label for the property that makes quarks respond to the strong force. Physicists could have chosen different names, but red, green and blue were convenient because three visible colours can combine into a neutral-looking mixture. The comparison is useful for keeping track of combinations, though the quarks themselves do not glow like tiny traffic lights. Every quark carries one of three colour charges. An antiquark carries a corresponding anti-colour. The basic rule is that particles which can travel freely over ordinary distances must be colour neutral. A proton achieves this by combining three quarks in a state whose colours cancel overall. A neutron does the same. A meson combines a quark with an antiquark so that colour and anti-colour cancel. The individual ingredients carry colour, while the completed particle does not. This is rather different from electric charge. An electron can travel alone while carrying negative electric charge. A proton can travel alone while carrying positive electric charge. Nature allows electrically charged particles to exist freely. Colour charge is not given the same freedom. No isolated red quark or green quark has ever crossed a detector. Whenever a quark is produced, it becomes part of a colour-neutral group before it can be observed. The force between colour charges is carried by gluons. A quark can emit a gluon and change its colour. Another quark can absorb that gluon and change colour in response. The total colour balance remains correct throughout the process. The quarks continually exchange gluons, and the exchanges transfer energy and momentum through the proton. The language of emission and absorption can create an image of small objects throwing smaller objects back and forth like a game of catch. That picture can help at first, but the quantum reality is not made from clear little trajectories. Quarks and gluons are excitations of fields. The fields extend through the region of the proton, and possible exchanges contribute to the full quantum state. There is no single permanent gluon that can be identified as the one holding two particular quarks together. Gluons also carry colour charge themselves. This is the feature that gives quantum chromodynamics much of its unusual behaviour. A photon carries electromagnetic energy, but has no electric charge. Because of this, photons do not directly attract or repel one another in the ordinary electromagnetic theory. Gluons carry the type of charge involved in their own force, so one gluon can interact with another gluon. That difference may sound small, but it changes nearly everything. If the messengers of a force can respond to one another, then the field creates additional field activity. A quark affects nearby gluons. Those gluons affect other gluons. The new gluon arrangements affect the quarks again. The interaction becomes a linked system rather than a simple message passed between two independent particles. Imagine a group of people trying to deliver instructions across a room. In a simple system, one messenger carries a note from one person to another and the job is finished. In the strong interaction, each messenger can also stop, exchange notes with other messengers, rewrite parts of the instructions, and recruit more messengers. Before long, the delivery system has become the main event. This is one reason calculations involving gluons can become so demanding. There are 8 independent gluon states. The number comes from the ways colour and anti-colour can be combined, while respecting the mathematical structure of the theory. It might seem that 3 colours and 3 anti-colours should give 9 possibilities, but one combination does not behave as a colour-carrying gluon, and is removed from the set. The remaining 8 form the force-carrying family. The exact colour carried by a quark does not change the type of quark it is. An up quark remains an up quark whether its colour label is red, green, or blue. Its electric charge, basic mass, and flavour remain the same. Colour is another property, separate from flavour. This gives each quark several identifying features at once, rather like a person having a name, an age, and a coat colour without any one of those being the whole person. Quantum chromodynamics also obeys a symmetry connected with colour. This means that the laws do not prefer one colour label over another. If all the colours were relabeled consistently, the physical predictions would remain unchanged. Red is not stronger than green, and blue is not given a more comfortable seat inside the proton. The labels are interchangeable as long as the rules connecting them are preserved. This colour symmetry determines how gluons interact. It is not an optional decoration placed on the theory after the particles were discovered. Once the symmetry is chosen, much of the force structure follows. The possible gluon exchanges, their self-interactions, and the requirement of colour conservation all emerge from the same mathematical framework. The strong interaction is called strong because, at the scale of atomic nuclei, it is much more powerful than electromagnetism. Two quarks inside a proton experience an interaction capable of keeping them confined despite their rapid motion and the enormous internal pressure. Yet the strength of this force is not fixed. It changes depending on the distance and energy involved. This changing strength is one of the most important rules in quantum chromodynamics. At very short distances, quarks interact more weakly. At larger distances within a proton, the interaction becomes stronger. The property is called asymptotic freedom. The name means that quarks approach a condition of greater freedom as the energy becomes extremely high and the distance becomes extremely small. This may sound backwards. In ordinary life, moving two objects closer usually makes their interaction stronger. Magnets pull more strongly when brought together. Electrical forces become stronger at shorter distances. Quarks behave differently because gluons carry colour and interact with one another. Their self-interaction changes the way colour charges distribute around a quark. A quark is surrounded by quantum fluctuations. Gluons appear in the field around it, and those gluons can produce further gluon activity. The combined effect tends to spread and alter the visible strength of the colour charge. When a quark is examined from farther away, more of this surrounding field is included, and the strong interaction appears larger. When it is examined at extremely short range, less of the surrounding activity contributes, and the quark behaves more nearly like a free particle. The strength therefore runs with energy. Running is the term physicists use when a quantity takes different effective values at different measurement scales. The underlying theory remains the same, but what an experiment sees depends on how closely it probes. A similar effect occurs with electric charge, though the direction is different. Quantum fluctuations partly screen the electric charge of a particle. At shorter distances, less screening is included and the electric force can appear slightly stronger. In quantum chromodynamics, gluon self-interaction produces what is sometimes called anti-screening. The effective colour force becomes weaker at short distances and stronger at larger ones. Asymptotic freedom made it possible to connect quarks with the point, like objects seen in high-energy scattering experiments. When electrons struck protons with enough energy, they appeared to scatter from relatively free constituents. This would have been difficult to explain if the strong force remained overwhelmingly powerful at all scales. Quantum chromodynamics showed that at the tiny distances reached by the collision, quarks could behave almost independently for a brief moment. Almost independently does not mean truly free. After the collision, the quarks still cannot escape as isolated particles. As they move apart, the strong interaction grows. Energy accumulates in the gluon field between them. New quark and antiquark pairs are produced, and the outgoing energy becomes a collection of colour-neutral particles. This process creates particle jets. A high-energy quark or gluon produced in a collision does not arrive at a detector alone. Instead, it leads to a narrow spray of hadrons travelling in roughly the same direction. By measuring the energies and directions of these hadrons, physicists reconstruct information about the original quark or gluon. Jets provide strong evidence that quarks and gluons are real physical ingredients. The particles in the detector form patterns predicted by quantum chromodynamics. Quark-initiated jets and gluon-initiated jets show statistical differences because gluons carry different color properties and radiate more strongly. No one sees a free gluon, but its presence leaves a recognizable trail. The strengthening of the force at larger distances leads toward confinement. Suppose we could attach an imaginary handle to a quark and begin pulling. At first, the separation would increase. The gluon field would become concentrated into a narrow region between the quark and the remaining color charge. More work would be required as the distance grew. In an electric field, separating opposite charges weakens their attraction. The energy cost eventually levels off enough that the particles can exist far apart. In the strong interaction, the field behaves more like a tube under increasing tension. The energy continues to grow with separation. Eventually, enough energy is stored to create a new quark and antiquark pair. One of the new particles joins the original quark, the other joins the remaining system. Instead of obtaining one isolated quark, we obtain two color-neutral hadrons. The attempt to pull the system apart has created more complete particles. The process resembles stretching a cord that refuses to leave loose ends. Pull hard enough and a new section appears, producing two finished cords rather than two exposed pieces. No ordinary material behaves exactly this way, but it captures the important result. Adding energy to separate quarks does not overcome confinement. It provides the energy needed to make new confined combinations. Confinement is firmly supported by observation, though deriving it in a simple, exact way from the equations of quantum chromodynamics remains difficult. The theory predicts the behavior, computer calculations reproduce it, and every experiment agrees that free quarks do not appear. Still, a complete mathematical proof of confinement is one of the great unsolved problems in theoretical physics. The difficulty comes from the strength of the interaction at proton scales. When a force is weak, physicists can begin with a simple picture and add corrections. Perhaps the first calculation includes one exchange particle, the next includes two. Later calculations include additional fluctuations. If each correction is smaller than the last, the total answer can be approached step by step. This method is called perturbation theory. It works extremely well for many high-energy processes in quantum chromodynamics, because asymptotic freedom makes the interaction weak. At the lower energies relevant to confinement and proton mass, the interaction is strong. The next correction may be as important as the first, and the one after that may be just as important again. The step-by-step approach loses its reliability. It is rather like trying to estimate the noise in a quiet cafe by considering one conversation at a time. When only a few people are speaking, the method works. In a packed room where everyone reacts to everyone else, adding one voice after another no longer captures what is happening. The crowd behaves collectively. The proton is a collective strong interaction system. Its quarks cannot be separated from the gluon field. The gluons cannot be treated as a small correction around otherwise free quarks. Every part is strongly connected to every other part. This is why the proton mass is difficult to calculate, even though the basic theory has been known for decades. Another important feature of quantum chromodynamics is that its characteristic mass scale is generated by quantum effects. At first glance, the theory of massless gluons and nearly massless quarks does not seem to contain a large built-in mass. Yet the strength of the interaction changes with energy, and that running introduces a particular scale at which the force becomes strong. This process is sometimes called dimensional transmutation. The name sounds severe, but the idea can be stated plainly. A theory that begins with a dimensionless interaction, strength can produce a physical energy scale through quantum behavior. That scale then determines the approximate masses and sizes of protons, neutrons, and other hadrons. The proton mass is therefore not simply copied from a mass already present in the original ingredients. Quantum chromodynamics produces its own scale. Once that scale is fixed by measurement, The theory predicts a wide range of particle masses and interactions. This is one reason physicists say that the strong force generates mass dynamically. The proton becomes heavy because the colour fields and confined quarks settle into a state whose energy is set mainly by the scale of quantum chromodynamics. The light quark masses slightly adjust the result, but they do not provide the main number. The vacuum of quantum chromodynamics also plays an important role. In everyday speech, a vacuum is empty space. In quantum field theory, the vacuum is the lowest energy state of the fields, and it is not empty in the simple sense. Quark and gluon fields possess fluctuations even when no proton is present. The strong interaction vacuum has a complicated structure. Pairs of quarks and antiquarks contribute to collective patterns. Gluon fields also possess non-zero activity. When a proton exists, it is formed within this active quantum environment rather than placed into a completely blank background. One major effect is connected with a symmetry involving light quarks. If the up and down quarks had no basic mass, certain left-handed and right-handed forms of the quark fields would be treated independently by the equations. The vacuum does not preserve this symmetry in the obvious way. It develops a pattern that links the two forms. This is known as spontaneous chiral symmetry breaking. The full phrase is less relaxing than the physical idea. A symmetric set of rules can produce a lowest energy state that chooses a particular arrangement. A perfectly balanced pencil standing on its tip has symmetry, but when it falls, it chooses one direction. The rules did not prefer that direction, yet the final state does. In quantum chromodynamics, this vacuum structure affects the behavior of light quarks and contributes to the properties of protons, neutrons, and pions. It is another reason the elementary quark masses do not tell the whole story. The quarks move through and interact with a strongly structured quantum background. Pions are especially important evidence for this symmetry behavior. They are much lighter than most other hadrons because they are connected with the broken symmetry. Their small but non-zero masses reflect the fact that up and down quarks are light, rather than exactly massless. The same theory must explain both the heavy proton and the relatively light pion. This is a demanding test. Quantum chromodynamics succeeds because the two particles receive their properties from different aspects of the same strong interaction. The proton contains 3 valence quarks, but quantum chromodynamics describes far more than those 3. The gluon field can produce quark and antiquark pairs. These pairs can annihilate back into gluons. Different arrangements overlap in the proton's quantum state. A physicist describing a fast-moving proton often speaks of Proton distributions. These distributions show how the proton's momentum is shared among quarks, antiquarks, and gluons. The distributions change with the energy scale of the experiment. At higher resolution, more gluons and C-quarks become visible. This does not mean that the proton has one fixed inventory that changes whenever a detector is switched on. Quantum field theory does not always assign a permanent particle count to an interacting system. The useful description depends on the scale of observation. What remains stable are the total charge, mass, spin, and other measurable properties of the proton. The gluons carry a large share of the proton's momentum. The C-quarks carry part of it. The valence quarks carry the net flavour and electric charge, but they do not carry everything else alone. This distributed structure is exactly what quantum chromodynamics predicts. The theory also explains why colour-neutral particles can still interact. Protons and neutrons contain no net colour charge, but their internal fields can produce a residual force over very short distances. This is similar in spirit to the way electrically neutral atoms can attract one another, even though their total electric charges cancel. The residual strong force binds protons and neutrons inside many atomic nuclei. It is weaker and reaches farther than the direct colour force between quarks. At the nuclear level, physicists often describe it through the exchange of particles such as pions, rather than through individual gluons. This change of description does not mean that a new unrelated force has appeared. It means that different scales call for different effective pictures. At the deepest level, quarks and gluons follow quantum chromodynamics. At the level of nuclei, protons, neutrons, and exchanged mesons provide a more practical language. Physics often works through layers of description. A weather forecast does not track every air molecule. A discussion of sound does not need to follow every atom in the speaker. The deeper rules remain important, but the useful objects change with scale. Quantum chromodynamics is the deeper rulebook beneath nuclear physics. It explains why protons and neutrons exist, why they have nearly the masses they do, and why they exert residual forces on one another. Nuclear models then use those particles as ingredients when describing atomic nuclei. Testing this rulebook requires many different experiments. Deep inelastic scattering reveals quarks and gluons inside protons. High-energy collisions produce jets. The rates of particle production test the predicted strength of the interaction. Heavy particle decays reveal how gluons are emitted. Collisions of heavy nuclei create quark-gluon plasma and test the theory under extreme temperatures. The predictions agree with an enormous range of data. At high energies, quantum chromodynamics is one of the most precisely tested theories in science. The running of the strong interaction has been measured across many scales. Jet patterns match the expected colour factors. Particle production rates follow the calculated behaviour. At lower energies, where direct calculations are harder, lattice quantum chromodynamics provides another route. The theory is placed on a grid, and computers calculate how quark and gluon fields behave. The grid acts as a temporary framework for the calculation, rather than a claim that space is physically made from little cubes. The computer samples many possible field configurations. From these, physicists extract the masses of particles, decay behaviour, and other properties. The calculations require enormous resources because the number of possible arrangements grows rapidly, especially when light quarks are included accurately. As computers and algorithms improved, lattice calculations became increasingly precise. They reproduced the observed proton mass and the masses of many related particles. This showed that the known quark masses and the rules of quantum chromodynamics were enough to generate the hadron spectrum seen in nature. The result is a major achievement. A proton is not treated as a particle whose mass must be entered separately. It appears as a state of the quark and gluon fields. The energy of that state can be calculated, and the answer matches the proton measured in experiments. Quantum chromodynamics therefore explains how a massless gluon field and very light quarks produce a heavy proton. Color charge determines the interaction. Gluon self-interaction causes the force to run with energy. The force becomes weak at short distances and strong at larger ones. Strong coupling confines the quarks. Confinement forces substantial momentum and field energy into a tiny region. Quantum effects create a natural mass scale. The combined state appears as the proton. None of these rules acts alone. Asymptotic freedom allows quarks to appear nearly free in high-energy experiments. Confinement prevents them from escaping at ordinary energies. Gluon self-interaction produces both behaviours. The quantum vacuum changes how light quarks behave. The generated scale sets the weight of hadrons. This is why the strong force can seem to have two personalities. Seen extremely close up, it loosens its grip. Seen at the scale of a full proton, it becomes powerful enough to trap every colour-charged component. The same theory produces both results without changing its basic laws. The next question is how this confinement works in practice, and why no experiment, no matter how energetic, has ever delivered a lone quark. Pulling harder does not open the proton in the way a container can be opened. The added energy changes into new particles, leaving colour charge hidden once again. Following that process more closely will show why confinement is not merely a force holding the proton together, but one of the main reasons its internal energy becomes a permanent part of its mass. Trying to remove a quark from a proton sounds, at first, like a straightforward experiment. if a proton contains quarks, then enough force should pull one of them out. We can separate atoms. We can split atomic nuclei. We can break molecules into individual atoms and take mechanical objects apart until their pieces are scattered across the floor, usually beside one screw that appears to belong nowhere. It seems reasonable to expect that a proton could also be opened, allowing its quarks to emerge as separate particles. Yet every attempt to do this produces the same curious result. The proton can be disrupted, new particles can be created, great amounts of energy can be released into detectors, but no isolated quark ever appears. This is confinement, one of the defining behaviours of the strong interaction. Quarks carry colour charge, and colour-charged objects are never observed alone under ordinary conditions. They remain confined inside colour-neutral particles such as protons, neutrons and mesons. A quark may be struck with enormous energy and sent rushing away from its original companions, but before it can travel a measurable distance as a free particle, the strong field reorganises the energy into new colour-neutral combinations. Confinement is not simply a matter of the force being very strong. A sufficiently strong ordinary force can still be overcome if enough energy is supplied. A spacecraft can escape a planet by moving fast enough. An electron can be removed from an atom if it receives enough energy. A nucleus can be broken into smaller nuclei. The strong interaction behaves differently because the energy used to separate quarks changes the system in a way that prevents a lone quark from emerging. To see why, imagine two opposite electric charges. They attract one another. Pull them apart and work must be done against that attraction. As the distance grows, however, the electrical force becomes weaker. Eventually the charges can be separated by a great distance, and the remaining attraction becomes extremely small. The energy required approaches a limited value. Quarks do not experience this simple decline. At very short distances, the strong interaction between them becomes relatively weak. As their separation increases, the interaction grows stronger. More and more energy is stored in the gluon field between them. The force does not gently fade as the quarks move apart. It resists the separation with increasing determination. The field between colour charges is often described as forming a flux tube. Instead of spreading evenly through the surrounding space, the strong field becomes concentrated into a narrow region connecting the separating quarks. This tube contains energy. As it becomes longer, the stored energy increases. A loose comparison can be made with stretching an elastic band. Pull the ends apart and the band stores energy. The farther it stretches, the harder it pulls back. But the strong field has an unusual response when enough energy is added. An elastic band eventually snaps and leaves two broken ends. A colour flux tube does not leave two bare colour charges. The energy creates a new quark and antiquark pair. One new particle joins the original quark at one end. The other joins the remaining colour charge at the opposite end. The flux tube has not released a lone quark. It has divided the system into two complete colour-neutral particles. The energy supplied to free a quark has instead produced additional matter. This is possible because energy can create particles. When enough energy is concentrated in the strong field, a quark and antiquark pair can appear. The new pair carries mass, momentum, and the appropriate charges. Colour is rearranged so that every final particle remains neutral overall. Suppose a meson contains one quark and one antiquark. If we try to pull them apart, the field between them grows in energy. Eventually a second quark and antiquark pair appears. The original quark combines with the new antiquark, while the original antiquark combines with the new quark. One meson becomes two mesons. No free quark is obtained. The process inside a proton is more complicated because the proton contains a 3-quark valence structure surrounded by gluons and C-quarks. Yet the same principle applies. Strike one quark hard enough, and it begins moving away from the rest of the system. The strong field follows. New pairs form. The departing quark becomes part of a new hadron, while the remaining colour charges reorganize into other hadrons. This conversion of quarks and gluons into observable color-neutral particles is called hadronization. It occurs very rapidly after a high-energy collision. Quarks and gluons produced in particle accelerators do not travel directly into the detector. They generate sprays of hadrons that arrive in groups known as jets. A jet contains many particles moving in roughly the direction of the original quark or gluon. The detector records their energies, directions, charges, and types. Physicists then reconstruct the likely properties of the initiating parton. The quark itself remains confined, but its motion leaves a clear experimental signature. This can be compared with following the path of a person through deep snow. The person may already have left the scene, but the trail shows where they travelled. A jet is far more complicated than footprints, because the original quark has become part of the particles in the trail. Still, the pattern allows scientists to infer what began the process. Different initiating particles produce different jet patterns. A gluon carries a stronger colour charge arrangement than a quark and tends to radiate more strongly. Gluon jets are often broader and contain more particles than quark jets. These differences match the predictions of quantum chromodynamics and provide strong evidence for the colour structure of the theory. The fact that no isolated quark reaches the detector is not due to weak equipment. Modern particle accelerators produce collisions with energies vastly greater than the proton mass. If confinement were merely a barrier with a sufficiently high but fixed energy cost, those machines should eventually overcome it. Instead, increasing the energy produces more particles and more complex jets. The harder the proton is struck, the more clearly its quarks and gluons influence the collision, but the final observable products remain color neutral. Energy reveals the internal structure without delivering its colored constituents as free objects. The proton can be opened only in the sense that its energy is redistributed into other confined systems. This behavior helps explain why quark mass cannot be measured by placing an isolated quark at rest. There is no free-up quark that can be trapped, slowed, and compared with another particle. Quark masses must be inferred from the behavior of hadrons, particle collisions, and theoretical calculations. Confinement also makes the simple idea of adding the quark masses incomplete. If the quarks could exist freely, one might imagine measuring each one separately and then assembling a proton. But the assembly cannot begin with three isolated light quarks. The strong interaction is already part of any observable state containing them. A proton is not created by taking free quarks and fastening them together. Quarks emerge from high-energy processes already within a colour field that immediately organises them into hadrons. The confined state is not a later modification. It is the form in which the quarks can exist as observable matter. There is a useful distinction between confinement and ordinary binding. The electron in a hydrogen atom is bound to the proton by electromagnetic attraction. Add enough energy and the electron can be removed. The proton and electron then exist separately as free charge particles. Their individual identities remain intact. A quark bound inside a proton cannot be removed in the same way. Add energy and the particle arrangement changes. New quarks appear and new hadrons form. The original quark may become part of a different hadron, but it never becomes a free color-charged object. This difference is one reason the proton mass belongs to the whole strong interaction system. In hydrogen, we can measure a free proton and a free electron, compare their total mass with the bound atom, and identify the relatively small effect of electromagnetic binding. For the proton, there is no corresponding measurement of free valence quarks before confinement. The small quark mass parameters come from the underlying theory, while the observable proton already includes the full energy of the confined fields. The energy cost of confinement contributes directly to the proton mass. The quarks are restricted to a tiny region. Quantum mechanics then requires substantial momentum. The gluon field stores energy. The self-interaction of gluons strengthens the colour field at larger distances. All these effects establish the characteristic energy of the proton state. Confinement also determines the proton size. If the quarks spread much farther apart, the field energy would increase. If they were compressed into a much smaller region, their quantum momentum would rise. The stable proton sits in a balance between these tendencies. The quarks do not occupy fixed points at a particular distance from one another. The proton is described by a quantum state spread across many possible field configurations. Yet the balance produces a characteristic radius and a definite mass. The particle maintains these properties even though its internal arrangement is constantly fluctuating. A common illustration shows three quarks connected by narrow tubes of colour field. This can be helpful, but it should not be mistaken for a literal snapshot. In a real proton, gluons interact with one another, C-quarks appear, and the field structure changes. The connections do not form permanent strings tied to labelled particles. The full quantum state includes many overlapping possibilities. At one moment in a simplified description, a gluon may be emitted. In another contribution, a quark and antiquark pair may appear. The measurable proton is the result of all allowed processes combined according to quantum rules. Confinement belongs to this complete field behaviour. It is not a rope placed between three otherwise independent quarks. The gluon field and the quarks together create a state in which colour cannot escape. Why the strong interaction confines colour so completely is one of the most profound questions in mathematical physics. Quantum chromodynamics is believed to contain confinement naturally. Computer simulations reproduce it, experimental observations support it, and no contradiction has appeared. Yet deriving confinement from the theory in a fully rigorous mathematical proof remains extremely difficult. This difficulty has earned the problem a place among the most important unsolved challenges in mathematics. A successful proof would show, under strict mathematical conditions, how a theory containing massless gluons can produce a gap between the energy of the vacuum and the lightest observable excitations. This is connected with the appearance of massive particles such as protons, and with the absence of free colour charge. The phrase mass gap describes the fact that the lowest excited observable states have a non-zero mass, even though the fundamental gluon field is massless. Empty space represents the lowest energy state. The next possible colour neutral states require a definite amount of energy. There is no continuous series of free low-energy gluon states appearing as ordinary particles. The proton is not the lightest possible hadron, but its mass reflects the same broad phenomenon. Quantum chromodynamics generates massive colour-neutral states from fields whose fundamental carriers have no rest mass. Confinement and the mass scale of the theory are closely connected. The strong interaction creates its characteristic scale through the running of its coupling. At very high energy, the force becomes weak. As the energy decreases, the effective strength grows. Eventually, it reaches a region where quarks and gluons can no longer be treated as nearly independent. Hadrons emerge as the useful observable objects. This transition is not controlled mainly by the up and down quark masses. Even if those quarks were exactly massless in the underlying equations, confinement would still generate massive hadrons. Their exact masses would differ, but the strong force would still create a non-zero scale. That is the heart of the proton mass mystery. The quarks are light, and the gluons are massless, but neither can exist freely at proton energies. Their confinement forces the system into an energetic state. The energy required by that state is measured as mass. One might ask whether the strong field is pulling the quarks together or preventing them from separating. Both descriptions are partly useful. The field resists separation, but the proton is not a static arrangement held together by simple inward pulling. Quark momentum creates outward pressure. Gluon fields contribute both energy and stress. The stable particle results from the total balance. The proton can also be excited. Add energy without completely disrupting it, and the fields can enter a higher state. The result is a heavier baryon resonance. These excited particles usually decay quickly into lighter hadrons. The existence of these resonances resembles the higher tones of an instrument. A confined system supports different allowed patterns. The ordinary proton is the lowest stable state with its particular properties, while excited patterns contain additional energy and therefore additional mass. This comparison helps clarify why confinement does not merely add a fixed binding force, it defines the entire spectrum of possible particles. Different quark flavors, spins, and field arrangements produce different hadrons. Quantum chromodynamics determines which states are allowed and how much energy each one carries. The particle zoo that once puzzled physicists became understandable through this structure. Protons, neutrons, pions, kaons, and many heavier particles are not unrelated fundamental objects. They are different confined states of quarks and gluons. Confinement organizes matter into a limited set of observable combinations. 3 quarks form baryons. A quark and an antiquark form mesons. More unusual combinations, including states with 4 or 5 valence constituents and states dominated by gluons, can also occur under the rules of color neutrality. Experiments have found strong evidence for several exotic hadrons. Even these unusual particles do not contain free color. Their internal arrangements may be more complicated, but the complete object remains neutral. Confinement does not insist that every particle must look exactly like a proton. It insists that exposed color charge cannot survive as an isolated observable object. In extreme conditions, confinement can be altered. Shortly after the beginning of the universe, temperatures were high enough for matter to exist as quark-gluon plasma. High-energy collisions between heavy nuclei can recreate this state for a tiny fraction of a second. In quark-gluon plasma, quarks and gluons are not locked inside separate protons and neutrons. They move through a larger shared region. Yet even here, they do not behave as a simple gas of completely independent particles. The interaction remains strong, and the plasma flows collectively like a remarkably smooth fluid. When the plasma cools, hadronization occurs. Quarks and gluons become confined into protons, neutrons, mesons, and other hadrons. The free-looking phase ends before any isolated color charge can reach a detector. This shows that confinement can depend on temperature and density. Under extreme conditions, the usual boundaries of individual hadrons dissolve, but color does not become an ordinary freely observable charge. The quarks remain part of a strongly interacting medium and eventually return to color-neutral particles. Inside neutron stars, matter may reach densities where quarks behave in unusual collective phases. Physicists study possibilities such as quark matter and color superconductivity. The exact conditions in the deepest cores remain uncertain. Even there, color charge is expected to organize itself according to the rules of quantum chromodynamics, rather than appearing as isolated quarks drifting through empty space. For ordinary matter, confinement is complete. Every proton in your body has held its quarks for as long as that proton has existed. The quarks have never quietly wandered into neighboring atoms. The gluons have never leaked out as beams of free strong force radiation. The color structure remains sealed within hadrons. This makes the material world remarkably stable. If quarks could escape easily, protons and neutrons would not persist. Atomic nuclei would lose their foundations. Matter as we know it would be impossible. Confinement is therefore not merely an odd rule encountered in accelerator experiments. It is one of the reasons the universe contains durable atoms. The chair remains a chair because its nuclei remain intact. Those nuclei remain possible because protons and neutrons remain stable. Those particles remain stable because their quarks and gluons form confined states. The same mechanism that prevents quarks from escaping also traps the energy responsible for most of the proton's mass. The motion cannot simply drain away. The gluon field cannot disperse into space. The proton's internal energy is locked into the stable color-neutral system. This gives confinement a double role. It holds the particle together and it turns internal energy into a lasting mass. The strong interaction does not merely stop pieces from separating. It creates the energetic object whose weight becomes part of every nucleus. Even when a proton is destroyed in a high-energy collision, its mass energy does not vanish. It becomes the energy and mass of new particles. Quarks are rearranged. Gluon fields produce additional pairs. The original proton is gone, but color confinement continues in the products. Nothing emerges from the collision carrying one exposed fraction of electric charge associated with a single quark. Detectors instead record complete hadrons with charges built from confined combinations. The rule survives even in violent events involving energies far beyond those found in ordinary matter. This has been tested in countless collisions. If free quarks existed, they would leave distinctive tracks because of their fractional electric charges. Experiments have searched for such signals in accelerator data, cosmic rays, ordinary materials and other environments. No convincing isolated quark has been found. The absence is not a gap waiting casually at the edge of measurement. It is consistent with the entire structure of quantum chromodynamics. Jets, hadron production, scattering results, and lattice calculations all point toward confinement. Yet the fact that confinement is supported so strongly does not make calculating its consequences easy. The strong interaction at proton scales involves too many linked field configurations for simple approximation methods. To predict the proton mass directly, physicists must account for a vast collection of possible quark and gluon arrangements. This is where powerful numerical calculations become essential. Rather than attempting to follow one neat diagram of three quarks connected by gluons, scientists allow computers to sample the fluctuating fields across a simulated region. From this collective behavior, the proton appears as a stable energy state. The calculation must reproduce the effect of confinement without inserting the proton mass as an answer. It must begin with the rules of quantum chromodynamics and the small quark masses, then allow the fields to generate the much larger observed value. Achieving this required decades of theoretical development, improved algorithms, and increasingly powerful computers. The proton was easy to weigh experimentally, but extraordinarily difficult to build from the equations. The next part of the story follows that effort, showing how physicists turned a theory of invisible confined fields into a numerical proton, whose calculated mass agrees with the particle found in nature. The proton was weighed long before anyone knew how to calculate its mass from the particles inside it. Experimental physicists could trap charged particles, study their motion in electric and magnetic fields, compare their behavior with electrons and other particles, and determine the proton's mass with extraordinary precision. The number was available. The difficulty was explaining why nature had chosen it. Once quarks were discovered and quantum chromodynamics became the accepted theory of the strong interaction, the problem seemed as though it should become easier. Physicists now knew the ingredients and the rules. Unfortunately, knowing the rules of a complicated system does not always mean that its final behavior can be worked out with a pencil and a quiet afternoon. Quantum chromodynamics describes quarks, gluons, color charge, and the strong force. At extremely high energies, its calculations can be remarkably precise. The interaction becomes weak enough for physicists to begin with a relatively simple process and add smaller corrections one after another. This works well for many collisions in particle accelerators. A quark emits a gluon. Another gluon is exchanged. Additional possibilities are included. Each improvement moves the answer closer to the observed result. At the scale of a proton, the interaction becomes too strong for that approach to remain dependable. The quarks are not almost free. The gluons interact intensely with the quarks and with one another. Temporary quark and antiquark pairs contribute. Confinement ties every part of the system together. No single process can be treated as the main event while everything else waits politely in the background. The proton is therefore easy to describe in a sentence and extremely difficult to calculate. It contains a net combination of 2 up quarks and 1 down quark, together with gluons and a sea of temporary pairs. But that sentence does not tell a computer how every field arrangement contributes to the particle's total energy. The number of possibilities is enormous. Each quark can carry different momentum. Each gluon field can take different forms. Every part influences the others through the strong interaction. For years, physicists faced an unusual situation. They trusted quantum chromodynamics because it explained high-energy experiments, particle jets, and many patterns among known hadrons. They also understood in broad terms that the energy of quarks and gluons should produce most of the proton's mass. Yet calculating the actual mass directly from the theory remained beyond the simplest methods. It was like having the correct recipe, knowing every ingredient, and still being unable to predict whether the result would be a loaf of bread or something requiring a polite apology to the kitchen. The method that eventually made the problem manageable is called lattice quantum chromodynamics. The word lattice refers to a grid. Instead of treating space and time as perfectly continuous during the calculation, physicists divide them into a large collection of closely spaced points. Quark fields are represented at the points, while gluon fields connect to neighbouring points. The continuous quantum world is temporarily replaced by a fine computational framework. This does not mean that physicists have proved that space is really made from tiny cubes. The lattice is a mathematical tool. It turns an impossible continuous calculation into a very large but finite numerical problem. Once the calculation is complete, the physicists study what happens as the grid spacing becomes smaller. If the method works properly, the result approaches the prediction of the continuous theory. The idea was developed during the 1970s, when quantum chromodynamics itself was becoming established. Kenneth Wilson showed how the strong interaction could be placed on a lattice while preserving its essential colour symmetry. His approach provided a practical way to investigate confinement, the region where ordinary high-energy approximation methods fail. The first lattice calculations were extremely limited by modern standards. Computers were slower, memory was smaller. Simulations used rough grids and simplified versions of the theory. Some calculations ignored the full effect of temporary quark and antiquark pairs because including them required far more computing power. This was known as the quenched approximation. The name may sound as though the computers were given a refreshing drink, but it meant that certain quantum fluctuations involving C-quarks were left out. The gluon fields were allowed to change, while the influence of virtual quark loops was simplified. This made the calculations possible, but it also introduced errors. Even these early simulations produced encouraging results. They showed that a theory containing light quarks and massless gluons could generate heavy hadrons through strong interaction energy. The proton did not need an undiscovered massive object hidden inside it. The general scale appeared from the dynamics of the fields. As computers improved, physicists began including C-quarks more realistically. These are often called dynamical quarks because their quantum effects are allowed to influence the gluon configurations. The calculations became much more expensive. Every possible quark fluctuation affected the probability of a field arrangement, and the computer had to account for this repeatedly across the entire lattice. A realistic simulation begins with the basic rules of quantum chromodynamics and a small set of input parameters. These include the strengths associated with the strong interaction and the masses of the quark flavors being represented. The values are adjusted using selected experimental measurements. The computer then predicts other quantities, including the masses of many hadrons. This detail is important because the phrase calculated from first principles can be misunderstood. Physicists do not begin with absolutely no measured information and cause the proton mass to emerge from pure logic. The theory contains parameters that must be connected with the physical world. A small number of measured quantities are used to set those parameters and establish the scale. Once that is done, the theory can predict a much larger collection of particle properties. It is similar to tuning a musical instrument before playing. The tuning does not determine every melody that follows. It establishes the scale. The structure of the instrument and the actions of the player then determine the notes. In lattice quantum chromodynamics, a few physical inputs set the theory, while the complicated field dynamics produce the hadron spectrum. The computer does not follow one proton as though it were a tiny mechanical model. It generates many possible arrangements of quark and gluon fields across the lattice. Quantum theory assigns different weights to these arrangements. Some contribute strongly, others contribute very little. The simulation samples the configurations according to their importance. This sampling is usually carried out through methods related to probability and random numbers. The computer explores one field arrangement, then another, gradually building a representative collection. The process is called Monte Carlo sampling, named after the famous centre of gambling because chance is used as a computational tool. The physicists are not gambling with the answer, although after several months of supercomputer time they may feel emotionally invested. Each individual configuration looks noisy and complicated. The useful physical information appears only after many configurations are combined. Patterns begin to emerge from the average. The proton is identified through the way certain carefully chosen signals behave across the simulated lattice. To create a proton signal, physicists construct a mathematical operation with the same quantum properties as a proton. It must have the correct electric charge, spin, and quark flavor. This operation is applied at one region of the lattice, allowing the simulated fields to produce every state compatible with those properties. The calculation then examines how the signal appears at another point separated in the time direction of the lattice. Many possible states can contribute. Heavier excited states fade more quickly in the calculation. At sufficiently large separation, the lightest state with the proton's properties dominates. The rate at which the signal decreases reveals the energy of that state, and that energy gives the proton mass. No tiny ruler or scale appears inside the computer. The mass is extracted from the behavior of quantum correlations. The proton emerges as a stable pattern in the field data rather than as a picture of three balls joined by lines. To make this procedure reliable, physicists must deal with several sources of error. The lattice spacing cannot be too large, or fine details of the fields will be lost. The simulated box cannot be too small, or the proton will be affected by its artificial boundaries. The quark masses must be realistic. The number of sampled configurations must be large enough to separate the true signal from statistical noise. Early calculations often used up and down quarks that were heavier than their physical values. Light quarks are computationally difficult because they create long-range fluctuations and make the numerical algorithm slower. Physicists calculated hadron masses at heavier quark values and then estimated how the results should change as the quarks approached their real masses. This introduced uncertainty. The extrapolation depended on theoretical guidance, and small errors could affect the final proton mass. Later calculations used lighter and eventually nearly physical up and down quarks directly. This reduced the distance between the simulated world and the real one. The strange quark also matters. Although a proton has no net strange valence quark, strange quark and antiquark pairs can appear in its quantum sea. Modern simulations commonly include up, down, and strange quarks as active dynamical fields. Some also include charm quark effects when the required precision makes them relevant. The calculations must also correct for the finite box. A real proton exists in continuous space without repeating boundaries a few tiny distances away. A lattice simulation usually represents a box whose edges are connected in a regular mathematical way. If the box is too small, fields extending from the proton can interact with their own repeated images. Physicists run simulations with different box sizes and calculate how the result approaches the infinite volume limit. They also use different lattice spacings and determine how the mass approaches the continuous limit. Several calculations are often required before one trustworthy physical answer can be reported. The the computational cost can be enormous. Lattice quantum chromodynamics has used some of the world's most powerful supercomputers. Thousands of processors may work together to update gluon fields, solve the equations governing quark motion, and store vast collections of field configurations. A single realistic calculation can involve repeated operations on large mathematical objects across millions or billions of lattice points and links. Improving the precision slightly may require a much larger increase in computing time. The proton is tiny, but persuading a computer to reproduce it accurately is not a tiny assignment. By the late 20th century, lattice calculations were already producing recognizable patterns of hadron masses. Protons, neutrons, mesons, and heavier baryons appeared in approximately the correct relationships. The results supported the belief that quantum chromodynamics was generating the mass scale of ordinary nuclear matter. During the following decades, the accuracy improved. Dynamical quarks were included, lattice spacings became finer, simulated volumes became larger, algorithms became faster. Quark masses moved closer to their physical values. Different research groups used different methods and compared their results. By the late 2000s, major calculations were reproducing the masses of a broad range of hadrons with striking agreement. The proton and neutron emerged near their measured values, along with many mesons and strange particles. The agreement showed that the standard model's strong interaction was sufficient to explain the observed hadron spectrum. This was one of the great quiet successes of modern physics. There was no single dramatic moment in which a detector flashed and announced that the missing proton mass had been found. Instead, years of theoretical work, numerical improvement, and computer calculations gradually closed the gap between the equations and the real particle. The result confirmed that the proton's mass is not mostly an unexplained input. It can be generated from quantum chromodynamics. Light quarks with small elementary masses interacting through massless gluons form a confined state whose energy matches the heavy proton measured in laboratories. Physicists can test the calculation in more than one way. A successful theory should not reproduce only the proton. It should also reproduce the neutron, pions, kaons, and many other hadrons. Each particle has a different quark arrangement, spin, and internal field structure. Matching the whole collection is much harder than fitting one number. Quantum chromodynamics passes this test impressively. Once the parameters are set, the lattice predicts a pattern that resembles the real hadron spectrum. Heavier quark combinations produce heavier particles. Different spin arrangements shift the energy. Symmetry relationships appear where expected. This broad agreement is powerful evidence that the proton mass comes from the known strong interaction, rather than an unknown hidden component. A mistaken theory might be adjusted to match one particle. Matching dozens of related particles with a common set of rules is far more convincing. The calculations also allow physicists to explore what would happen if quark masses were different. The simulated up and down quark masses can be changed, and the proton's response can be measured. As the elementary quark masses decrease, the proton becomes somewhat lighter, but it does not approach zero mass. Even in a theoretical limit where the light quark masses vanish, quantum chromodynamics still produces a massive proton-like state. The exact value changes, and the relationships among hadrons change, but most of the mass remains. This is direct computational evidence that the strong interaction generates the main weight dynamically. The quark masses do contribute. Their effect can be studied by measuring how the proton mass changes when those input masses are adjusted. This relationship gives information about quantities known as sigma terms. These help estimate the direct contribution of quark mass to the proton. The light up and down quarks account for only a small part. Strange quarks can contribute indirectly through C effects, though determining the exact amount requires careful calculations. Heavier quarks influence the proton through quantum processes involving gluons, even though they do not sit inside it as permanent valence ingredients. The remaining mass is associated with quark energy, gluon field energy, and a quantum effect often called the trace anomaly. The name sounds as though the proton has misplaced something suspicious, but it refers to a deep feature of quantum chromodynamics. If the light quarks were massless, the classical version of the theory would not contain an obvious preferred mass scale. The equations would look similar when distances and energies were rescaled. Quantum effects break this scale symmetry. The strength of the interaction changes with energy, producing the characteristic scale of confinement. The trace anomaly is one formal way of expressing how this quantum breaking of scale symmetry contributes to the proton mass. It is closely connected with the energy stored in gluon fields and with the running of the strong interaction. Different theoretical decompositions divide the proton mass among quark energy, gluon energy, direct mass terms, and the anomaly in slightly different ways. This is why a perfectly simple pie chart of proton mass can be misleading. One chart may say that a certain percentage comes from gluons, another may assign part of the same physics to the anomaly, and another may organize the energy according to a different calculation scheme. The total proton mass remains the same. The division into named pieces depends on the chosen definitions. The slogan that almost all proton mass comes from the strong interaction is reliable. The claim that one exact fixed percentage belongs permanently to one individual category requires more caution. Quarks and gluons form an interacting quantum state, and their contributions cannot always be separated like coins placed into different jars. Lattice calculations can also investigate the proton's internal structure. They estimate how momentum is shared, how quarks contribute to spin, how charge is distributed, and how the proton responds to external fields. These predictions can be compared with scattering experiments. The agreement is not perfect in every quantity. Some calculations remain difficult, and some experimental measurements still contain uncertainty. But the overall framework has become a working precision tool rather than a rough qualitative idea. Other approaches complement the lattice. Deep inelastic scattering shows how quarks and gluons share momentum inside a fast-moving proton. Electron-proton collisions reveal charge distributions. Experiments involving the production of heavy particles test gluon behavior. Measurements of special scattering processes offer information about internal pressure and stress. No single experiment places labels on portions of the proton and weighs them separately. The answer emerges from many connected observations interpreted through quantum chromodynamics. Lattice calculations provide the bridge between the underlying field theory and the measurable proton. The calculation also explains why the proton mass is stable. The proton corresponds to the lowest energy state with its particular quantum properties. Higher states exist, but they are heavier and decay. The ordinary proton cannot simply lose most of its internal field energy and remain a proton because no lighter version with the same identity is available. The energy generated by confinement is therefore locked into the particle's existence. It does not leak away as heat or radiation. The proton can move, collide, and exchange energy with other particles, but its rest mass remains fixed unless the proton itself is transformed or destroyed. This makes the proton mass a form of organized quantum energy. The word organized is important. A random collection of quarks and gluons does not automatically form a proton. Their color, spin, flavor, momentum, and field configuration must combine into the correct stable state. The lattice calculation searches through the allowed quantum possibilities and identifies that state. The final number is not produced by adding 3 quark masses. It is obtained from the energy of the full configuration. This success changes the meaning of the original question. Physicists were not searching for a missing heavy ingredient. They were learning how apparently light ingredients can form a heavy object when confined by a self-interacting quantum field. The mass was never absent from nature. It was absent only from the simplest description. When a proton is introduced as 2 up quarks and 1 down quark, the statement identifies its valence content but leaves out the dynamics. It is like describing a hurricane by listing a few air molecules. The ingredients are real, but the behaviour of the whole system carries the main explanation. Lattice quantum chromodynamics restored that missing behaviour. It included the fluctuating gluon fields, the sea quarks, the confinement, and the collective energy. Once those were allowed to act according to the strong force, the proton became heavy naturally. The result also offers one of the clearest examples of emergence in fundamental physics. The underlying particles do not individually possess the property in the amount seen in the final object. Their interaction creates a new scale. The proton's mass belongs to the whole. This is not emergence in a vague or mystical sense. It is calculated through a precise theory. Change the input parameters and the resulting mass changes. Refine the lattice and the answer approaches a stable limit. Compare the prediction with experiment and the numbers agree. The same approach now supports research across nuclear physics, particle physics, and cosmology. It helps calculate the behaviour of rare particle decays, the forces between nucleons, the properties of matter at high temperature, and the effects of possible particles beyond the standard model. Yet the proton remains one of its most important achievements because protons make up such a large fraction of the visible universe. Reproducing their mass means explaining much of the mass in stars, planets, oceans, living organisms, and everything else built from atomic nuclei. The calculation begins in an abstract grid filled with numbers representing quantum fields. It ends with the mass of the object at the centre of nearly every atom. Somewhere between those two lies the connection between the invisible rules of the strong force and the weight of the familiar world. The proton's missing mass was therefore not found in a newly discovered particle or a hidden chamber inside the nucleus. It was recovered by taking the known quarks and gluons seriously enough to calculate their collective behaviour. The answer was in the motion, the confinement, the field energy, and the quantum scale created by the interaction itself. That answer carries us beyond the proton. If most ordinary mass is generated by internal energy rather than supplied directly by elementary particle masses, then the solidity of the visible universe has a surprisingly dynamic origin. The next step is to look outward from this tiny calculation and ask what it tells us about matter as a whole, about the role of the Higgs field, and about why a universe made from nearly massless ingredients can contain stars, planets, and living bodies with weight. The answer to the proton mass puzzle begins inside one particle, but it does not stay there for long. Once we understand that most of a proton's mass comes from the energy of quarks and gluons, rather than from the small basic masses of the quarks themselves, the explanation spreads outward. It reaches atomic nuclei, stars, planets, living cells, and nearly every object that can be placed on a scale. The proton reveals that the mass of ordinary matter is not mainly a collection of heavy elementary pieces. It is the result of light particles becoming trapped in a powerful quantum interaction and forming stable structures whose internal energy appears as mass. This changes the way we can think about the material world. A stone feels heavy because gravity pulls on its mass, and because that mass resists acceleration when we try to lift it. Most of the stone's mass lies in the protons and neutrons inside its atomic nuclei. Most of the mass of those protons and neutrons comes from quantum chromodynamics. The weight in your hand can therefore be traced back to quarks moving inside confinement, gluon fields carrying energy, and strong interactions maintaining stable particles. The stone does not feel active. It may have remained in the same place for years, apart from the occasional person moving it and immediately wondering why they did so. Yet its apparent stillness rests upon an internal activity occurring inside every proton and neutron. The matter looks quiet because the quantum systems are stable, not because their interiors have stopped. A proton has a mass almost 100 times greater than the combined basic masses of its 3 valence quarks. The exact comparison depends on how quark masses are defined, but the main result is clear. only a small portion comes directly from the Higgs-related masses of the up and down quarks. The rest comes mainly from the energy generated by the strong interaction. This does not reduce the importance of the Higgs field. The Higgs mechanism explains why elementary particles such as electrons and quarks have basic masses. Without those masses, the universe would not simply look the same with slightly lighter objects. The balance of particle reactions would change. The properties of atoms and nuclei could become very different. Chemistry might not develop in the familiar way. The electron receives all of its known rest mass through its interaction with the Higgs field. The top quark receives a very large mass because it interacts strongly with that field. Up and down quarks interact much more weakly and are therefore light. These differences affect which particles are stable and how matter can be assembled. The proton, however, shows that the Higgs mechanism is only one part of the mass story. It provides the small masses of the quarks, while quantum chromodynamics produces the much larger mass of the bound proton. The two mechanisms work together, but they should not be confused. When the Higgs boson was discovered, it was sometimes described as the particle that gives mass to everything. This was a useful shortcut, but it left out the fact that most visible mass comes from the strong force. The Higgs field gives basic mass to the quarks. It does not directly supply the full weight of the proton. A useful comparison is a small group of musicians and the sound they produce together. The musicians must exist before the performance can begin, and their individual instruments matter. Yet the sound filling the room is not simply the combined weight of the instruments. It is produced through organized motion and interaction. Inside the proton, the quarks provide the necessary ingredients, while the strong field creates the much larger energy of the complete state. The proton also reminds us that mass is a property of systems. It does not need to belong only to indivisible particles. A collection of particles can have a total mass determined by motion, binding, pressure, and stored field energy. The whole can be much heavier or slightly lighter than a simple sum of separately imagined ingredients. Atomic nuclei provide a familiar example of a system becoming slightly lighter through binding. A nucleus normally has less mass than the combined free protons and neutrons from which it could be assembled. When the nucleus forms, energy is released. The bound nucleus contains less total energy and therefore less mass. This nuclear mass difference powers stars. In the Sun, hydrogen nuclei take part in a chain of reactions that eventually produces helium. The resulting helium nucleus has slightly less mass than the original collection of particles. The missing mass leaves as energy, much of which eventually reaches space as sunlight and heat. The energy released in nuclear fusion is significant, but it represents only a small fraction of the original proton mass. Most of the mass remains locked within the protons and neutrons of the helium nucleus. The strong interaction inside each nucleon continues to provide most of the total. This gives us two levels of mass energy at once. Quantum chromodynamics creates most of the proton and neutron mass. Nuclear binding then changes the combined mass by a smaller amount when those particles form a nucleus. Stars use the smaller difference while preserving most of the larger strong interaction mass. Every sunrise therefore depends on a subtle rearrangement of particles whose own mass was largely created through quark and gluon dynamics. The process begins with the strong interaction inside protons, continues with nuclear reactions inside the Sun, and ends with photons reaching Earth after travelling through space. Those photons have no rest mass, yet they carry energy. When absorbed by matter, their energy can increase the mass of the receiving system by an extremely small amount. Plants use sunlight to build chemical structures. Solar panels convert it into electrical energy. A warm surface contains slightly more internal energy than a cold one. The same relationship between mass and energy appears at every scale, but the proton is where it becomes responsible for most ordinary matter. It is a compact example of energy becoming part of a stable object. The neutron tells a similar story. It contains one up quark and two down quarks, rather than the proton's two up quarks and one down quark. Its mass is slightly greater than the proton's. Most of that mass also comes from the strong interaction. The small difference between proton and neutron mass has enormous consequences. A free neutron can decay into a proton and other particles. A free proton cannot decay into a neutron without receiving additional energy. This helps make hydrogen stable. If the relative masses were changed, the early universe might have produced a very different mixture of nuclei. Stars could burn differently. Stable atoms might be less common. A difference that seems tiny compared with the total mass of a proton helps shape the large-scale composition of the cosmos. The elementary quark masses contribute importantly to this difference. The down quark is heavier than the up quark, which tends to make the neutron heavier. Electromagnetic effects inside the particles push in another direction. The final neutron-proton difference emerges from a competition between these contributions. Without the small masses supplied through the Higgs field, the balance would change. The proton might still remain massive because quantum chromodynamics would continue generating strong interaction energy. But the stability of protons, neutrons, and nuclei could be altered. This is why it would be misleading to say that the Higgs field contributes almost nothing. It contributes little to the numerical mass of a proton, but it helps determine the structure of the world in which that proton exists. A small ingredient can have a large effect if it changes which state is stable. Salt contains only a small amount of some trace substances, yet one unpleasant spoonful too many can dominate the entire meal. Particle physics is more precise than cooking, fortunately, but the general warning survives. A small contribution to mass can still be essential to matter. The proton stability is another central part of the story. No confirmed proton decay has ever been observed. Some theories predict that protons may eventually decay, but experiments show that any such lifetime must be vastly longer than the age of the universe. This stability allows matter to persist. Atoms can survive for billions of years. Rocks can form planets. Gas clouds can become stars. Molecules can build cells. None of this would be possible if protons disappeared quickly. The strong interaction creates an object that is both energetic and stable. The energy does not cause the proton to fly apart because confinement prevents the quarks from leaving as isolated particles. The proton occupies the lowest available state with its particular conserved properties. The material universe is therefore built from stable patterns of quantum fields. The objects we call particles are not necessarily tiny pieces of solid substance in the classical sense. They are repeatable states with definite properties. Every proton is identical to every other proton. A proton in your body has the same charge and mass as a proton inside a distant star, as far as experiments can determine. Their internal quantum fields may be involved in different environments, but the basic particle remains the same. This uniformity is remarkable. Matter can be assembled reliably because its ingredients do not vary from place to place. Oxygen atoms in your lungs behave like oxygen atoms in a laboratory because their nuclei contain the same number of protons. Those protons are governed by the same strong interaction everywhere. The proton mass also sets an important scale for chemistry. Electrons are much lighter than protons, so atomic nuclei remain nearly fixed, while electrons arrange themselves around them. This separation of masses helps make the mathematical description of atoms manageable and allows stable molecular structures to form. If electrons were as heavy as protons, atoms would behave differently. If protons were much lighter, nuclear and chemical scales would shift. The particular mass hierarchy of known particles helps produce the world of molecules. Chemistry itself depends mainly on electrons, but the mass of chemical matter resides mainly in nuclei. When two atoms form a bond, their electron arrangements change while the proton masses remain almost entirely unchanged. The resulting molecule may release or absorb energy, producing a tiny change in total mass, but most of the original mass remains inside the nucleons. A glass of water therefore receives nearly all its weight from protons and neutrons, even though its behavior as water comes from electrons and electromagnetic forces. Its mass and its chemistry emerge from different levels of physics working together. The hydrogen atoms contribute protons. The The oxygen nucleus contains protons and neutrons. The electrons determine how the atoms bond. The strong interaction creates most of the nuclear particle mass. Electromagnetism shapes the molecule. Gravity pulls the glass downward. Several fundamental interactions cooperate to produce one ordinary drink. The proton also connects the present universe with its earliest moments. Soon after the universe began expanding, conditions were too hot for protons to exist as stable individual objects. Matter formed a quark-gluon plasma, in which quarks and gluons moved through a larger, strongly interacting environment. As the universe expanded, it cooled. Quarks and gluons became confined into hadrons. Protons and neutrons appeared. At that stage, the strong interaction generated the massive particles that would later form atomic nuclei. Within the first few minutes, some protons and neutrons combined into light nuclei. Most protons remained as hydrogen nuclei. Much later, after the universe cooled further, electrons joined nuclei and created neutral atoms. Gravity gradually gathered matter into clouds. The mass of protons and neutrons caused these clouds to attract one another and collapse. The first stars formed. Their interiors created heavier elements through nuclear reactions. When massive stars died, they scattered carbon, oxygen, iron, and other elements into space. Later stars and planets formed from this enriched material. The atoms in living organisms were assembled through a long history that depended at every stage on the stable mass of protons and neutrons. Most of the mass in your body was therefore generated by the same strong interaction that operated when protons first formed in the early universe. The quarks inside those protons may have been rearranged through countless nuclear processes, but the underlying mass mechanism has remained unchanged. The visible universe contains stars, gas, dust, planets, and living matter. All of this represents only a fraction of the total matter and energy inferred by cosmology. Dark matter appears to contribute far more mass than ordinary atomic matter, though its identity remains unknown. Dark energy dominates the current energy budget of the universe in another way. The proton does not explain dark matter or dark energy. Its lesson concerns ordinary visible matter. But within that visible portion, the strong interaction is responsible for most of the mass. This distinction is useful. Saying that quantum chromodynamics explains most of the mass around us does not mean it explains every form of mass in the cosmos. Whatever dark matter is, it may receive mass through a different mechanism. Black holes can contain mass from many forms of energy. Neutrinos have small masses whose exact origin remains an active question. Physics often provides several answers to the same broad question, because mass can arise in several ways. Elementary particles can gain mass through fields such as the Higgs field. Composite systems can gain mass from internal energy. Gravitational systems can have total masses influenced by binding and radiation. The proton offers one especially important example, rather than one universal explanation for everything. Still, its importance is difficult to overstate. Ordinary objects contain enormous numbers of protons and neutrons. Their generated mass gives planets enough gravity to become round. It helps stars compress their cores until nuclear reactions begin. It gives bodies inertia and allows stable structures to resist changes in motion. When you take a step, your muscles push against the ground and accelerate the mass of your body. Most of that inertia belongs to protons and neutrons. When Earth holds you to its surface, gravity acts on the energy contained in your matter. The familiar feeling of having weight is connected to the strong force working inside particles too small to see. Even a decision to remain in bed has a relationship with proton mass. The bed supports the gravitational pull on countless nucleons, while their inertia makes sudden movement less appealing. Physics is not responsible for every delayed morning, but it does provide a respectable explanation for why getting up requires work. The proton also teaches us not to confuse emptiness with inactivity. An atom contains large regions without ordinary particles sitting at fixed points. A proton contains quantum fields rather than solid miniature objects. Yet the fields carry energy and produce measurable mass. The world is not built from tiny hard pieces alone. It is built from interactions, fields, stable states, and relationships between energy and motion. This does not make matter less real. It explains why matter has the properties we observe. A proton can collide with another proton, bend through a magnetic field, participate in a nuclear reaction, or remain bound inside an atom. Its mass is measurable and consistent. The fact that most of that mass arises from internal energy does not make it an illusion. It makes mass a richer property than the everyday idea of stored material. This lesson appears elsewhere in physics. The mass of a nucleus depends slightly on its binding energy. The mass of an excited atom is greater than the mass of the same atom in a lower energy state. A charged battery has more mass than a discharged one. A warm object has more mass than a cold one. The changes in ordinary systems are tiny because their added energies are small compared with the rest. Mass already contained in their protons and neutrons. The proton is where internal energy dominates rather than merely adjusting the total. This is why our daily intuition works as well as it does. When we add objects together, their masses appear to add directly because each object already contains enormous, strong interaction mass. The small changes from heat, chemical bonds, and motion are usually too slight to notice. A loaf weighs approximately the sum of its ingredients because every ingredient already contains protons and neutrons carrying their generated mass. The chemical energy released during baking changes the total by an amount far below the sensitivity of the kitchen scale, which may already be struggling with a little flour beneath one corner. At the deeper level, the proton shows that the simple additive picture was built on top of a more complicated process. Before masses can add like ordinary objects, quantum fields must first create the stable particles that carry those masses. This gives the strong interaction an unusual role. It is not only a force acting between pre-existing objects, it helps create the observable objects themselves. Quarks and gluons become protons, neutrons, and other hadrons through confinement. The energy of the interaction becomes part of each particle's identity. Gravity then responds to the resulting mass. Electromagnetism arranges the particles into atoms. Nuclear forces bind many protons and neutrons together. Chemistry builds molecules. Biology organizes some of those molecules into living systems. Each level depends on the level beneath it but introduces new behavior. A cell cannot be understood by listing quark masses. A proton cannot be understood by treating it as three isolated quarks. Nature builds complexity through organized interactions. The proton is a clear example because the difference between ingredient mass and total mass is so large. Nearly all of its weight comes from the collective system. The particle is not merely a container, it is an ongoing quantum state. Physicists continue studying the proton because several details remain difficult. They want more precise maps of its gluons, C-quarks, spin, pressure, and internal momentum. New colliders and improved experiments will probe how these properties change at different energy scales. The basic origin of its mass is well established, but understanding the internal accounting in complete detail remains an active field. Different theoretical descriptions divide the mass contributions in different ways. Lattice calculations continue becoming more precise. Experiments continue testing the distributions of quarks and gluons. The proton has been known for more than a century, yet it remains a major research subject. Familiarity does not guarantee simplicity. Sometimes the most common objects are the ones hiding the deepest structure. Nearly every atom contains protons. Nearly every solid object receives most of its mass from them. Yet each proton is a compact system governed by a theory that requires some of the world's most powerful computers to calculate accurately. That contrast is one of the quiet pleasures of physics. A common particle can lead to questions involving quantum fields, symmetry, confinement, supercomputers, and the early universe. The weight of a cup can be connected to the self-interaction of massless gluons. We began with a mismatch. The proton was heavy, while its quarks were light. Adding the quark masses left almost the entire value unexplained. Gluons had no rest mass, so they did not appear to solve the puzzle in the ordinary way. The missing mass came from abandoning the idea that mass must be hidden inside heavy ingredients. Quarks carry enormous internal momentum because they are confined. Gluon fields store energy and interact with themselves. Quantum fluctuations fill the proton. The strong interaction creates a stable energy scale. The total energy of this confined state appears as proton mass. The answer is therefore both simple and strange. Most of a proton's mass comes from the energy of the strong force. It comes from motion, fields, confinement, and quantum dynamics. It belongs to the whole particle rather than to one small piece. This is what the proton reveals about matter. The visible world is heavy mainly because energy has been organized into stable quantum structures. The universe does not need elementary particles with large masses to build massive objects. It can begin with light quarks and massless gluons, then use interaction to create protons, nuclei, atoms, and everything assembled from them. So the next time you lift a book, carry a bag, or feel the pull of your own body against the ground, the weight is not mainly coming from tiny lumps of basic mass. It is coming from countless confined systems, each filled with quarks and gluons following the rules of quantum chromodynamics. The surfaces remain still. The nuclei remain hidden. The protons continue their internal activity without sound, heat, or visible motion. They have done so since the early universe, and will continue for longer than any human timescale can easily describe. And perhaps that is a comfortable place to leave the question for tonight. Matter feels solid, steady, and familiar, while most of its mass comes from a world of motion that never stops. The proton sits quietly at the center of the atom, carrying a small positive charge and an unexpectedly large mass, while inside it the strong force holds light particles in an energetic state that gives weight to almost everything we know. If you have listened this far, you're now a little more familiar with the hidden activity inside ordinary matter. The room around you has not changed, but its weight may seem slightly less ordinary. The bed, the walls, the air, and your own body are built from particles whose mass is mostly the energy of quarks and gluons held together. And as the details begin to soften and the day moves farther away, there is no need to keep every term or every particle carefully arranged in memory. It is enough to remember the main idea. The proton is heavier than its ingredients because the interaction between those ingredients carries energy, and that energy becomes mass. The material world is not made heavy by stillness. It is made heavy by stable activity hidden inside every nucleus. So let your thoughts settle. Let the quarks remain confined where they have always been, and let the gluons continue their work without any supervision from us. They have managed rather well so far.